And welcome everybody again. It's nice to see so many having signed up for this. As Shiva said, please really take advantage of this live webinar. I'm looking forward to receiving your questions, so we hopefully have a lively discussion over the course of the next 3 days. For the others that might not interact, so also maybe hello YouTube for the ones that watch at this at a later date. But first, I want to start at the basics, which is what is EEG for, or even shorter, what is EEG actually? For the Germans, so I regularly received news about the Erneuerbare Energiengesetz, which is not the one I usually associate with EEG. It's also not EEG. The short answer is EEG is, of course, an abbreviation for many things, but also mainly in this case for electroencephalography, which is kind of a mouthful. So instead of stumbling over the whole word, I usually try to stick to the abbreviated EEG. But to explain the whole term, it's made of 3 parts. Electro, which means electrical activity. Encephalos is in the head, or in this case, the brain. And graphy is originally writing, but also in a sense recording. So EEG literally means electrical activity recorded from the brain. And the basic idea behind EEG, why do we do all this actually, is how do we get from here, so some sort of brain reading, to here, so some sort of deeper understanding of the mechanisms of our mind, perception, feelings, attention, all these things going on in our head. Via this, so some sort of electrical activity was quickly lines recorded. And speaking about electrical activity, I also want to take the time shortly to introduce you or maybe reiterate some of the electrical terms you might already have heard. The 3 main ones here is voltage, resistance, and current. The one popular analogy is to think about this in the terms of water as well. So you could think of voltage being like the water pressure pushing water through a pipe. The resistance is the resistance of the pipe. So for example, the pipe diameter, or how much dirt is in the pipe maybe, that impedes the flow of the water. And the current is then the flow rate of the water through the system. And if everything is in the right balance, the volt pushes the current correctly through the wire. By the way, it also technically most often pushes it from the minus to the plus pole. So we kind of messed up the naming here, because intuitively you might think it comes from plus to minus, but most of the time it flows from minus to plus. And in this case, might light up a light bulb, for example. And with another situation here, you could also imagine if the voltage, so if the water pressure is reduced and the resistance stays the same, then there might not be enough pressure to push enough current through to light up the light bulb. So less voltage means there's less current. And vice versa, if you think about the wire or pipe diameter being reduced, so there's being more resistance, then the voltage might not suffice to push enough current through the wires to light up the light bulb. So in a very simple term, there won't be too many mathematical things here, but in a very simple way, the current flow is the pressure divided by the resistance. So the more pressure you have, or the more voltage you have, the more current you have, and the more resistance you have, the less current you have. One additional or 2 additional terms I want to introduce is AC/DC, and some of you might think about a rock band if you hear AC/DC, but it's the other way around. The rock band was named after the electrical terms, and DC in this context is direct current. And this is also what's happening in this example diagram. So the direct current means the current flows only in one direction, directly here from minus to plus, and nothing changes. And AC is an abbreviation for alternating current. So you could imagine the voltage source being flipped. So it flows in one direction and then the other direction, one direction and the other direction, basically back and forth. The most common alternating current we have is what's pouring all the electricity around us. It's usually 50 hertz or 60 hertz, which means this voltage flips around 50 or 60 times a second. But of course, we're not talking only about electricity, lighting up a light bulb, only metaphorically, maybe the metaphorical light bulb in our head, but we're talking about electrical activity from the brain. So the most basic building block of the brain are neurons, which transmit information in our brain. And you might have heard of neurons having an action potential. So basically, if a certain threshold is triggered, then the neuron delivers current basically from one end to the other end. But this is not actually the main source of EEG, but one step even closer, if you look at the presynaptic and postsynaptic membrane, so basically where two neurons meet, and then this is also called a synapse. That's where the communication is mediated. And if an action potential arrives at the presynaptic terminal, that leads to the release of neurotransmitters into this synaptic cleft, which diffuse into this cleft and reach the postsynaptic membrane, where they trigger an excitatory postsynaptic potential, which is also kind of a mouthful, so it's often abbreviated EPSP, excitatory postsynaptic potential, which is actually the main source of an EEG. So it's not the action potential itself. If you zoom out one step further, we also don't look at one neuron usually, but large groups of neurons that are summed up together. And why are they summed up together? Because they are organized in parallel, at least in some layers of the brain. So primarily in layers 3 and 5, they are organized in parallel. So the activity from the individual neurons nicely sum up. So you can then record an EEG signal, which is the summed up activity of lots of neurons firing together. If you zoom out one layer further, then the brain is also suspended in liquid or the cerebrospinal fluid, and the electrical activity has to pass through this and also in many other layers. So the different meninges, arachnoid mater, dura mater, pia mater, and then the skull and the scalp, and then some sort of like maybe you have some skin oils, and then electrode gel, and then finally the electrode, which is also mostly to say this electrical activity has to pass through a lot of layers before you can actually record it. And one final step, zooming out further, that you usually don't have just one electrode recording from the brain, but you have a whole configuration of many electrodes positioned depending on which region of the brain you're most interested in. And when do these neurons actually fire together? Another analogy here would be like observing a sports stadium from above. If you would imagine you would hover in the maybe VIP seat in a helicopter hovering above the stadium, you could not isolate any single person clapping or making noise. But you can only hear if a large group of people suddenly erupt in laughter or applause or whatever it is. Usually when something important happens in the stadium, for example, a goal is scored, and people start clapping because they're very happy, or maybe the others are very unhappy and might also make noise. But usually if something important happens, large groups of people or large groups of neurons will start making noise together. And when do they fire together? There are also two different ways of looking at this. One would be a summed up evoked response, which would basically be silence, no one claps, no neuron fires, nothing happens. And then something happens when everybody starts clapping, all neurons start firing together. But another option is also phase resetting of ongoing oscillations. So in most sports stadiums, if it's not a concert maybe, but if there's really sports going on, people are usually not that quiet. So they're usually making noise already if no goal is scored. But they're making noise not in a concerted effort, but everyone might have their own priority when to fire or when to clap. But only if something important happens, again, a goal is scored, people erupt in synchronized firing or synchronizing clapping. So phase resetting of ongoing oscillations is another option to trigger a large potential that can be read by the EEG on top of the head. If you now sum up this one large group of neurons that fire together, that's still just one group of neurons. And in a very simple term, you can think of it about it as a dipole. So a single source of neurons sitting on top of the head, for example, and all being oriented in the same way, perpendicular to the surface of the head. And we see this here from the left, from the right, top, bottom, front, and back, so from 6 different perspectives. Just as one group of neurons producing already a complex pattern on the top of the head. And you can see the time course here. So if we imagine this group of neurons firing together, this is an example brain reading you might get from EEG. So they start firing, so your voltage goes up, and then they stop firing, the voltage goes down again. And this is different depending on where on the head you actually measure this. So this is where you see it here on the right, that the CZ electrode is the electrode directly on the center of the head. So imagine this is just above the center of the neurons firing together. You see the largest deflection, but also in the sensors around it, you see still some of this effect happening to a lesser extent. And if you go even one ring further, you see the opposite, so a negative deflection. And the reason is that if there's a positive deflection somewhere on the head, there's usually also a negative part, because the brain itself doesn't get charged by it, but you only have differences. It's positive on one side, and it has to be negative on another side. If we now imagine this moving, let's see if I can get this to work, because the electrodes might not be positioned all in the same or all in this simple direction, but if you imagine these electrodes being positioned slightly offset, so not completely perpendicular, but a bit offset, you can see even though they stay at the same place, the resulting topography changes depending on their orientation. And if I also move this source now, for example, an auditory potential on the side, if I move it to the auditory cortex, more or less, you can also see that the resulting topography again changes to the right, and still depends on the orientation. So not just the place, but also the orientation of the neurons. So if I move this around, you can again see how the resulting topography changes. And going one step further, it's also usually not just one part of the brain that's firing. If you think about an auditory potential, so people hearing something, they often hear it from both ears if they have normal hearing. So we could imagine we have two sources, one on the left and one on the right. And they might also be slightly different. So they might be slightly different in their position, slightly different in their orientation, and also slightly different in the time course. So this time course here is very sharp and short, while the time course on the left is a bit broader and slower. And if you then record the resulting brain activity, you only see the summed up response of both sources at the same time. And one step further could also be a visual potential, which is in the back of the head. And now I simulated left and right, and I simulated on each side a positive and a negative deflection. So both on the right and on the left, you have this first positive deflection with a slightly different time course, and then slightly at another place, a negative deflection. So in taking these four sources together, now it slowly starts to look like a real EEG if you have already seen one. So you see this mostly posterior activity, but that's spread over the whole head still, but the largest deflection is posterior. And you'll see this time course, first the positive, then the negative deflection, then it goes back to baseline. But one important step that misses here is usually noise. So all kinds of other activities that we are not interested in. So these are the four interesting signals of interest, but you have millions of other sources in the brain doing all kinds of different stuff. And this is usually then just random noise. So that now it looks a bit more like real EEG with random noise added on top. So to sum up, our brain is also not, usually at least, a smooth surface, but it has valleys and peaks. And the peaks are also called a gyrus, and the valleys are called a sulcus. And if the activity is on the peak or the gyrus, you have the simplest way that the activity is strongest directly above the gyrus and also very centered and very strong. If it's oblique, so both on the gyrus and sulcus, it's weaker and also shifted to the side. And if it's only in the sulcus, then it's even weaker and also more shifted to the side. And the fundamental challenges of EEG remain that it's a tiny signal overlaid by multiple other signals, distorted by various influences and variable across subjects and trials. So in a sum, really hard to measure generally, but there are various ways to deal with that, which we talk through the whole next 3 days. One is to use good and appropriate EEG hardware, you use filtering, you use good study practices and piloting, pre-processing strategies and artifact removal. But the one thing I wanted to highlight here is averaging across trials and subjects. So going back to my first slide, it's not just one brain recording, but a huge amount of data you usually need to actually get from this brain reading to a sensible conclusion. And to fill this in with some example numbers, I put in an example EEG experiment here. For example, you might have 128 EEG sensors recording for 1,000 milliseconds, 100 repetitions of your stimulation you are interested in. You might record from 32 different subjects, and you are interested in the effects of 2 different conditions. And if you sum all of these up, it's about the order of magnitude of 1 billion data points. So it's a huge data set that you can't look at all at once. But instead, what you usually have to do is you have to average together some of these dimensions. Michael will talk later about trials, but I want to highlight some of the other dimensions here. So this is an example EEG you might see, also published, which in this case only looks at the two different conditions and only looks at the milliseconds on the time course. And it averages subjects, trials, and peak sensors. And the result is something like this. So you have two curves evolving over time from 0 to 1 second. And condition 1 and 2 are different. Specifically in this time period, it's around 400 milliseconds after a simulation happened. It's not important now what happens, but you can say, okay, the brain does something different in condition 1 than in condition 2, and this is where I see the difference. But you can also look at it in a different way. If you average the time I just shown you and instead look at all sensors, you might have something like this. So this is a topographic map which then colors the difference of the two curves we just saw in different colors. So if it's a blue color, it's a negative difference, and a yellowish color is a positive difference. And these correspond to each other. So these both show the same effect, that this time is averaged to this topography, and this topography is averaged to this time course. You can also go one step further. If you look at both the time and the sensors, you have a time course over, for example, 1 second, and you can see that this differences evolves over time. So it's not just the peak is there, but it arrives already earlier and also fades over time. And a lot of the times it's greenish, so not much effect visible there. And even one step further is if you would imagine looking at all 16 subjects, you have a huge data set. I don't want to highlight all of them, but just to a brief introduction here, for example, subject 1 has a much stronger effect than the average. And also the peak is slightly delayed, while, for example, subject 2 has a weaker effect, which is also a bit of a different time course. And all the other subjects all look different, but they look different but similar enough to reach conclusions. So in short, a single participant does not always show the representative signal. The orientation differs, the topography differs, so you need a lot of data and a lot of participants for general conclusions. So this is one example here. And to briefly sum this up, you need a lot of neurons, a lot of conditions and dimensions to get your results, but in the end, you will also distill them all down to a single or a few single averages to be able to make sense of this huge amount of data. And Michael will talk about more visualizations later as well. And I believe we have a short time for one quiz question. Shiva, if you can. So to test you, and not a test as this will not be graded, but basically test yourself if you know. If not, you can ask later. So one question here is EEG signals at an electrode originate from A, neural action potentials directly under the EEG electrode only, B, summed up evoked responses from many neurons, C, phase resetting of ongoing oscillations, and or D, all cells in the brain equally independent of orientation. And you might see the results. So most of you correctly said it's summed up evoked responses from many neurons, which is correct. A, neural action potentials directly under the EEG electrode is not technically fully correct because it's not the action potential and it's also not the EEG electrode or the neurons directly under the EEG electrode only. So it's kind of correct, but the main source would be the excitatory postsynaptic potential, so EPSP, and neurons directly under, but also in the vicinity. C is also correct. It could be phase resetting of ongoing oscillations. And D, again, is a bit formulated that way. All cells in the brain equally independent of orientation is also not quite correct. So it depends on the orientation, and it's also not equal for all cells. So it's primarily the pyramidal cells organized in parallel, and also primarily in the vicinity of the EEG electrode, but not only under it. But we will have time to discuss this later if you have questions for this. But first, Michael will take it away with more details about also the trial averaging and what the different potentials mean.
All right, thanks, David. I'm happy to take over. So in this second part, we're now going to look at a few different things. So first of all, I want to put EEG a little bit into perspective. EEG you have come across EEG now already, and we know this is from a resolution perspective, so that it has a low spatial resolution and a high temporal resolution. So that means we can precisely know when the activity is happening, but we can't know so well where the activity is happening. This is the case for both EEG and MEG. However, there are also other techniques like fMRI and fNIRS, which are actually the opposite. So they are rather having a high spatial resolution, while they do not have a very good temporal resolution. Besides these methods that are all non-invasive, so the electrodes or the measuring system is outside of the participant, there are also others that are invasive, like ECOG or LFP recordings, which have both a high temporal and a spatial resolution. But yeah, they are invasive, so this is usually only happening in patient studies. Let's put a few details together about the three non-invasive techniques. So EEG, you have already heard, high temporal and not so good spatial resolution. What we are measuring here, you just heard it from David, is that it's the electrical activity. So it's a direct measurement of what's happening in the brain. And at the same time, if you have seen an EEG system already, it's quite small, so it's rather portable and also affordable from a price perspective. Compared to fMRI, very different. So temporal and spatial resolution, basically the other way around. An fMRI machine is super big and expensive, so not portable at all, and yeah, quite expensive. So you can't just buy that quickly for the lab. And it measures something very different. It measures blood oxygenation, so it's hemodynamic metabolic signal. So this is an indirect measure of brain activity. fNIRS is a little bit in between, so it has a relatively high temporal resolution. The spatial resolution is not as good as fMRI, but much better than EEG, not so good for subcortical structures. From a price and mobility perspective, it's actually more similar to EEG, while this signal that is measured is more similar to fMRI. So it's also rather a metabolic signal. This means that all of these techniques, they complement each other a little bit. So as you can see, they have some advantages and disadvantages, and the other is the other way around. So you can imagine if you're putting these together in a multimodal imaging context, then you actually get the benefits of all of them. However, combining several techniques means also that you are actually having more challenges as well. Let's come back to the EEG signal. So it's just one measurement method. It offers, though, a variety of different analysis methods, and the goal is to find the right method to answer your research question. So with a single EEG recording, there are several things that you can look at. You can, for instance, look at the location where it's recorded. You have timing information. You have also frequency characteristics and the relationship between the signals if you look at them together. So the question is, what kind of effect are you interested in? Do you look for? And therefore, some of these analysis methods might be better suited. And we will now look at some of them. In brief, you can also think of it like this. So you first of all have the paradigm, which could be, for instance, event-related or a block design. You can also think about measuring in the electrode or the source space, and also you can think about the signal domain, and this is connected to specific analysis types. So I will look briefly into all of these, but we will focus on event-related potentials as a measure of choice for many EEG scientists. Let's start with the differentiation, though, between the two basic paradigm principles, event-related or trial-based designs and block designs, which can be used for analyzing states of brain activity. So you see here a continuous signal, or two rather, and we focus on the top one at first. It's very important in event-related designs that you get accurate markers indicating the event onsets. So here in this example, you see two types of markers. In red, there are stimulus markers for A and B, so for two classes of trials. And then in green, you see response markers. Those response markers you might not always have, because not in all experiments you are recording a response. If you think about what's important, said already, markers are important, so also coding them is important so that you know what is behind them. Also, you should think about trial numbers and also the duration of the trial so that you can capture the effects you're interested in. And if you want to make sure that there are no systematic errors in your design, you also want to avoid learning effects or habituation effects. So randomizing the order of trials is a pretty good idea. For the block designs, on the other hand, here it is the case that we are usually looking at something that goes on for a longer while. So like in the example here, a task or condition A that takes a while, and then the same for different tasks. So something like a resting state could be an example where you maybe just rest for a few minutes while recording EEG. However, the other considerations are very similar to event-related paradigms. How do you get, though, from the continuous data to the event-related potential? David already mentioned it a little bit. Let's look in more detail in this. The name implies event-related potential. It is activity that relates to an event. So it's evoked by a certain event happening. So in the experimental design, you hypothesize, given a certain task and the presentation of the stimulus, that you might detect some modulation of neural activity. And usually you would repeat this presentation or stimulation over and over again, and then you end up with a certain number of segments or trials. But you need to consider that each trial in your EEG recording does not only contain this evoked activity that you want to look at, but also this ongoing activity or noise, which might not have anything to do with your task. And what you are doing in order to come to this representative waveform, the ERP, is that you just average, as David already introduced. So you average all stimuli in the same category together. And the idea behind this is that the noise is not locked to the presentation of the stimulus. So it's a bit random, and therefore it's maybe positive in some trials, negative in some other trials, and therefore they will cancel each other out. And what remains in the ERP is the evoked activity. So you can extend this principle now to contrast two different events. Often you are interested in what happens in a category A compared to another one, which might be a controlled stimulus. And in a very simple experiment, you might then do this not just in one person, but in several participants. And then you are looking into the difference between these two ERPs for A and B on the individual level, but you can also look at it on the group level. And then you can look into this comparison of the EEG activity within a specific time interval between the conditions. To sum this ERP story up, so we are running an ERP analysis when we want to investigate the effects that a certain stimulus has on the ongoing EEG, and we would expect differences between stimulation conditions or experimental groups maybe. And we expect these differences to happen at specific time points. And therefore, we look at all of these numerous ERP components that you have probably heard of. Here are a few examples. What we can then do is that we can look at their amplitudes, the mean or the peak amplitudes, the latency, so when they are happening, but also we can create these topographies of ERP components that look over the scalp distribution. Let's have a quick look into ERP components. Each of the deflections within the ERP waveform represent a different stage of mental processing. So nomenclature first. Many ERP components, but not all, are named using a combination of the polarity and the time around which they peak, meaning a P300 refers to a positive peak around 300 milliseconds. If you look at the graphic here, think first of polarity. So in this case, you see plus is downward. This has been done for historical reasons a lot in ERPs. However, nowadays you also see it the other way around, which is more intuitive. So always check a graph for how it's plotted. And then also, if you look at the N2 here in the example, this is in the positive area, but the peak is more negative than the data before and after. So it's a relative negativity, so to say. You can look at ERPs in different time components here. So there are the very early sensory components like C1 or the auditory brainstem responses, which are happening super fast and are having very low amplitude. So you need very good resolution for these. And these are interesting if you're looking in quick sensory processing. Then we have a few slower sensory components, which are often interesting if you're looking in the analysis of stimulus characteristics. And then we're having these more long-lasting cognitive components. I'm showing here a very classical example, the P300 from an oddball design. You will see this more often in this workshop. So in this case, we're contrasting two stimuli, one that is occurring way more often than the other one, a standard and a target. And the P300 becomes more positive going if this target stimulus is just less predictable, much less predictable than the standard stimulus, and also if it's quite different. So think of two tones that are very different in pitch as a potential experiment. Okay, if you want to interpret ERP components, you should not think of them in isolation. You always should interpret them with respect to the task. So the complexity, the stimulus characteristics, but also maybe instruction factors. And you should also think of them depending on who you measure. So healthy adults versus patients. Some patient groups show quite differently looking ERPs, or also if you're looking maybe into older people, because that might also change the ERPs. And then also effects of the recording situation, for instance, and referencing. Okay. Now we're doing a short quiz to check what we've just learned. Shiva, could you please do the first question? Recommended design principle for an event-related paradigm is present all trials of one condition in a sequence, vary trial numbers between conditions, present trials from all conditions in random order, vary presentation modalities across conditions. As before, you have a few moments time to vote, and I see how the answers are coming in. So really just feel free to test yourself with these quiz questions. It's really just to check what we are doing in the workshop and if you're maybe got the information right. So now a lot of you have voted. So the majority of you gave the right answer, present trials in random order. That's important in order to avoid learning effects. Presenting all in one condition in a sequence, well, that's exactly the thing you shouldn't do unless it's more of a block design for a brain state. Vary trial numbers, not so good, because then the comparison basis is quite different. Vary presentation modalities as well, not so good, because then other effects are mixing in with the condition differences. Which features of an ERP peak can you directly read off from a plot? The latency of the peak, the connectivity at the peak, the amplitude of the peak, or the source of the peak? Let's look at the results. Yes, that's exactly what is right. So the latency and the amplitude of the peak, you can just read that off in the graph from this curve, the time point where it peaks and how tall the amplitude is. The connectivity, nobody answered. That's good because you can't. You really have to make an analysis for this. The source of the peak, well, depending on which electrode you're looking, you might be able to assume where roughly the source is, but this is really due to how the brain signal is traveling through the brain, not possible to just say from the electrode label where the source is from. Okay, sorry, then we can now continue and remove the quiz. Thanks. Just for the last few minutes, let's look at a few other ways to analyze your EEG signal, because now I talked about analysis in time with ERPs. At the same time, you can also think of an EEG as a mixture of oscillations of different frequency, and therefore you can also decompose the signal and look at those different frequencies. So in EEG research, we have this classical distribution of frequencies from delta to gamma, and the frequency ranges here, they should just give orientation. Across publications, you will often see rather different numbers here. And the frequencies, they are often connected to specific mental states, to specific things that the brain is doing functionally. For instance, if your eyes are closed while you're awake and you're relaxing, the alpha band activity goes up. One way of looking into frequencies is via Fourier analysis. Imagine you're having a signal that is made up of several oscillations of different frequencies, and then think of probing the signal with templates of different frequencies. And whenever a frequency is contained in the signal, you get a nice peak in this spectrum. So that's the spectral amplitude. However, you see already from the signal here, those oscillations, they are stable in time or stationary. And this is important because with such a frequency analysis with FFT, you do not contain time information. So you get one spectrum for the whole signal. This is something you might be doing if you want to look into the power in a specific frequency band, like alpha power. You can also look into frequency-specific topographies, but you should do this kind of analysis if you're interested in more static activity differences in the brain. So this is something that you can do nicely in a block design, for instance. However, if you're thinking of your ERPs again, where we are looking in time where something happens, you might also want to do that for the frequency. In that case, think about a signal like this, again made up out of different frequencies. However, they are modulated over time. So if I would now do an FFT analysis at different spots in the signal, well, the spectrum, they would look very different at the two times in your signal. So that's not so ideal. In such a case, you rather want to have something like this, which is a plot from a wavelet analysis, which is time frequency analysis. So something that preserves both time and frequency information. And here you can see an ERP and its time frequency analysis next to each other. So when you want to look in the frequency content of a signal that is transient in time and is changing over time, then this is the right thing to do. But actually you can get similar measurements like voltage or power values. Power, by the way, is voltage squared, and also time frequency specific topographies. Lastly, two very different kinds of analyses. So connectivity analysis is something where you want to look into the relationship between different sites where your signal is measured. There are different types of connectivity, but we often in EEG look at functional connectivity, for which you can't say, well, this goes in a specific direction, but there is just some kind of correlation. And one example analysis for this is coherence. You might have heard of this. If you have a very high correlation, or let's say perfect correlation, then you get a coherence value of 1, which means the two signals over time are in perfect synchrony. So then we assume that they're functionally correlated with each other. Last example analysis very different if you want to look beyond the scalp. So because normally we are measuring these electrical potentials, but we know they are coming from somewhere inside of the brain, and we can model this actually, how the neuronal current sources in the brain come to create this electrical potentials on the scalp. And if you have this kind of model, there are analyses where you can inverse model this, and you can come to where the actual sources are based on your scalp EEG. This is called source analysis. Here I show you just 2 example plots. They're from an analysis called Loretta, which is widely used, and you get these kind of similar to fMRI looking maps for this that are a bit blurry, but you can also get time courses of these sources inside of the brain as a result. To sum up, your research question should determine the experimental paradigm that you're using, the localization, so do you want to look at this in the electrode space or in the source space, and also which kind of analysis you want to apply for it. However, you can of course use also several analyses in combination, and you will hear this a lot. Textbooks and publications will give you a good idea of how to do this. And with that, we are actually done with this very first session of the workshop and have time for questions.
There are 3 related questions that are around the same point, so let me try to combine them. They relate to the sign of the EEG activity. So do the plus and minus in the whole brain activity, I think related, David, to your presentation, do they always sum up to 0? Is the question.
Yes, this will maybe also a bit clearer in the next talks, but basically it depends on the choice of reference, because we are already always recording a difference between 2 points, and it basically depends which points you choose to take a difference from. So I would not say it's arbitrary. It does have significance, where's plus and where's minus, but it's one what the brain does, and the other is how you arrange your electrodes. And if you, for example, take the difference from here to here, or if you take the difference from here to here, or if you take the difference from here to some people take the ears, for example, that's a different difference than if you take these 2 as a difference, and also it's a different difference if you take these 2 as a difference. So they sum up to 0, because I mean the brain should not get charged unless you rub a balloon on it or something. But it depends how you position your electrodes and which electrode you subtract from which other electrode.
Okay. And that, I think this question is related.
One more, maybe you can change it afterwards with Analyzer.
Yes, that's true.
By re-referencing.
Yeah.
This is a question, I think, related to sign, but it comes related to the ERP. And the question is, when you think about an ERP, how can we interpret negative and positive amplitudes? What exactly does it mean? Or do they have any specific meaning?
Actually, they don't really have a specific meaning. That is somewhat arbitrary. So what we are just looking is how the brain, kind of in correlation to what we are doing to probe it, reacts. And over time, with all these experiments, they have been repeated so many times that we just basically found, okay, this positive deflection around this time is correlated to be doing this and that. If you then look really well what is happening functionally in the brain at this time, and would really look at the source and how this is oriented, so similar to what David showed in this small simulation, then yeah, because of the source where it is, there will be a certain orientation of the signal, and therefore the curve will go into a certain positive or negative direction at this electrode. But it's not so really, I would say, a functional thing that we can say, oh, this has to be positive because the brain is doing this now, or it has to be negative because of the other way around. But generally also because the brain signals, they are oscillating the whole time, you always get also this up and down wavy pattern, and how these positive and negative ones are basically following each other in a sequence. So it makes more sense not so really to think about, oh, here's the brain now going positive, the ERP, or here's negative, and connect that to something, but rather look at it on the level of these specific components, because they specifically have been linked to certain things. And if they are positive or negative, and when they're happening, they will be all linked to something else, to something specific, and don't kind of try to put all positive components and all negative components into one and the same drawer, so to say.
Okay, because there's a nice question here. Let me try to rephrase it. That is linked to this. So it's about the interpretation of sign again and polarity. If the P300 is more positive in one group of electrodes, does it mean it will be more negative in a different set of electrodes at the ERP level?
I mean, it could be, if we are looking, let's say, depending on what David just explained about what the reference of the whole data is, if you're looking on the other side of the head to compare to the electrode we are looking at, then we will, of course, see a different picture here. However, this is something we are usually not looking at an ERP level. Usually for the P300, we know roughly from the literature, from experiments, where this is happening, where we see these effects exactly there. And therefore we are looking there, and we are looking for an effect that goes in a specific direction. So if you think about it of a proof of principle and say, well, I want to look in the other side and how it looks there, then you could see a different behavior of the two conditions that should kind of also be consistent. It's, of course, since the P300 is happening here, it's quite hard to look here because there is your neck. Yeah. Okay. I would rather really also, again, come from specific ERP components and come from the experience. Of course, maybe you're looking into something completely new and more explorative, and then it makes sense definitely to look into the field everywhere. How does the signal react in specific regions for this conditional difference? Yeah.
Okay. This is another very interesting question, and it unfortunately will be our last, but we can answer the rest of the questions that are pouring in the chat. So when you talked about noise cancellation, the question is, why don't you use a filter instead of averaging? Like, why not filter everything? Why do you need to average? Or should we average first and then filter?
Yeah, so we will have a whole section about filters, I think, on day 3, Yin-Fen and me. And in short, I would say filters have positive and negative sides. For one, you can definitely filter out signals you're not interested in, but there's always a trade-off that you have to have some filter artifacts, depending on which direction you filter, which filter settings you choose, and so on and so forth. But yeah, in general, I would say most published EEG research employs some sort of filter or looks at only specific frequencies and not all of them. But you should be careful how you choose your filters to not mess up your signal too much, and basically remove both the signal of interest and the noise, or distort your signal of interest and think it looks different than it actually does, because the filter, if you only filter in one direction, you have a filter artifact on one side. I will show some Yin-Fen as well. I will show some examples of. I think Yin-Fen shows the filters going right, and I will show some filters going wrong.
Okay.
On day 3.
Maybe just to add one sentence. Can I still, or are we too short?
Sure.
Okay.
A quick one.
ERP perspective, just to add to this. So think of it also, you can only filter stuff away you're not interested in, but that noise might also happen in the same frequency range as your signal of interest. So this averaging is also helping you to get rid of stuff that you just can't filter, because otherwise you would anyway filter out your signal of interest.
That's a great way to put it. So we will take a 5-minute break. Thank you very much. A very insightful session, and we'll be back in 3 minutes or so. Okay. See you soon, and please keep sending the questions. This is great.
I will talk or continue talking about EEG measurement principles and technology, part 1. Paulo will tell you in part 2 what to choose, but I will first tell you how it works. And how it works, like going back to my previous slide, is basically, how do we get from here, from the brain to here, to record this massive signal, massive data set? So how does this EEG hardware here work that gets us all this amazing data? And we'll talk later about the later steps. And regarding EEG, no EEG history talk can be done without mentioning Hans Berger, who was kind of a bit crazy German, but who nevertheless piloted the EEG technology, and with his first EEG recording attempts. You can see here on the left, one is one of his first subjects having like this large protruding sensors pouring out of his head, and here one of his first original string galvanometers. These galvanometers were originally meant to find faults in telecommunication lines and basically first repurposed to measure EEG from the brain. And you can see it's a very mechanical process. For example, at one here, you have the mechanical crank driving a motor. There were straw fiber markers that marked the electricity fluctuations on a piece of paper. And then, yeah, the paper was fed through, basically. One additional historic EEG amplifier is also here right next to us in Munich, in the Deutsches Museum Munich, where the head of Brain Products, Manfred Jaschke, also visited, I think, for the 100-year of EEG celebration. And you can see it's basically a huge suitcase or of a machine for just 2 EEG channels that had also huge tubes that were meant to record this process. So a very large amplifier for very, in this case, only 2 channels. And this is basically also how it started. So it started with very limited technology that was also very invasive. So also Hans Berger started recording directly from the brain with participants that had trepanation, so holes in the skull for other medical reasons. And he basically poked an EEG electrode in there. Later, it wasn't as invasive anymore. He also used needle electrodes without piercing the skull, but he still pierced the skin to really get the good signal. And one of his first famous recordings was this alpha rhythm. Like Michael talked about different frequencies already, but the alpha rhythm is also called alpha because it was the first signal that was recorded here. And you can see from his own son Klaus, im 15. Lebensjahr, so 15-year-old Klaus, had this around 10 hertz signal recorded from his brain. And the one a bit more advanced but still old machine you can see on the right. But this was already a multi-channel recording with many channels being recorded from the surface of the brain, but still on paper, a very analog process. And this is also from a very different kind of topic here, brainwaves, a cultural history of electroencephalography, which I won't go into detail here, but I just want to mention that for over 100 years now, people have not only researched this with hard science and new discoveries have been made, but this has literally changed the whole culture, that being able to record from the brain changed how we told stories. For example, how you can see EEG in movies, in comic books, in books, in different kinds of stories people tell, usually in a very reductive way. If it's some superhero with brain activity, that's not really how it happens, but still, because we have EEG, that changed the science, but it also changed the culture, basically. And you can find more examples in this cultural history book. But again, this was a very primitive technology at first, or not primitive, but repurposed technology at first. And the science always goes hand in hand with the technological development. And also Hans Berger, in his very first EEG publication in 1929, mentioned the same, where he wrote in a very convoluted, very German, long-winded sentence, which I translated here. It would, of course, also be desirable for the pursuit of these questions if even more sensitive instruments, such as those that technology is actually able to produce, could be used for these investigations. You can read the whole paper. It's also this kind of style that was popular back then. You have to talk complicated to be real science, I guess. But nevertheless, today we have much more advanced instruments. Just as one example, the LiveAmp is now our very small mobile amplifier that's non-invasive. You don't have to pierce the skin anymore, because it has a high amplifier input impedance that allows high electrode impedance. So it's much more comfortable for the participants. We don't record on paper anymore. We record digitally, which allows much more advanced analysis techniques. analysis techniques, also a hard word to pronounce. And we have a higher resolution and a trigger port for additional communication. And now I threw a whole bunch of technical terms at you, and this is precisely what I wanted to talk about as well. If you look at the spec sheet of any modern EEG amplifier, like the ActiveChamp over here, you see all kinds of different specifications: sampling rate, channels, bandwidth, input impedance, input noise, voltage range, resolution, common mode rejection. And I basically want to talk you through what these mean, and in the process explain how the amplifier works. And first, I want to start with the impedance. In this case, the high input impedance we have for the amplifier, and the low noise, which basically is the reason why we don't have to pierce the skin of participants anymore, to the benefit of both participants and us being able to recruit more willing participants, maybe, not just our own children that can't say no, maybe. And when talking about impedance, you might first know the electrode impedance, which is much more commonly talked about, because this is something you can influence in each individual recording, and you should measure in each individual recording. And impedance measurement is basically an indirect measure of how good the electrode is connected to the, or it's a measure of how good the electrode is connected to the participant, which is an indirect indicator of data quality. So it's not directly data quality. You can and still should look at your raw EEG signal to judge how good the quality is, but you can also check impedance to have an indirect measure of how good it's connected. And the way it works is you apply a low voltage through a voltage input electrode, for example, the ground electrode from the amplifier, that then flows through the conductive material, depending on the electrode type. Might be electrode gel, might be water, might even be dry. And then through the skin, sweat, hair, and moisture on the electrode side of the input voltage electrode. Then through the head surface, basically to the next electrode you actually want to measure. Again, through the conductive material on the measured electrode side, and then through the electrode back to the amplifier. And this is measured with an AC, so alternating current voltage. And that's also why we call it impedance and not resistance, because resistance is technically the opposition to both alternating and direct current, but we are only interested in the resistance, again, or opposition to alternating current, which is called impedance. And the low voltage has also two sides to it, so it's very low voltage, so it's imperceptible, and basically the participants don't feel it, and it's also non-threatening, so it doesn't hurt them. You don't feel it. The downside of that is it's only approximation, though it might be a few percent off. It's not an exact measurement where you can pinpoint it's exactly 11.5798 ohm or something, or kilo ohm, but it's around 10 kilo ohm, and that's already enough for you to know that the connection is good. But also, it is a flow through at least two electrodes. So you always have an input electrode, which is usually ground or reference, and then the measured electrode. So it's always two electrodes at least being part of this cycle, which means if the impedance is bad at the reference or ground electrode, no reliable measurement is possible, and your voltage flow might be much different than you actually expecting. So you should always first check that the reference and ground have good impedance before continuing measuring your other electrodes. I mentioned that there are different conductive material between the electrodes and the head, and that's precisely also what plays into the impedance levels, because we have different electrode technologies connected directly to the head. One is a passive electrode with abrasive gel, which literally scrubs away at least the outer layer of the skin. Still, no piercing, there should be no blood, but at least a little bit abrasion. Then we have active electrodes, which only use a viscous gel, which isn't abrasive. Saline solution, where you basically have a sponge with some saline water that connects to the skin. Or in the most extreme case, you can also have a direct skin contact with a dry electrode, as the name implies, without any gel, so directly putting it on the skin. So it's gel-based, sponge-based, or dry. And that's also kind of the target impedance levels you should have at your electrode site. So for the abrasive passive electrodes, you usually want to be low, maybe below 10 kilo ohms. Sometimes you can get away with a little bit higher. For the active electrodes, we target usually 25 kilo ohms. The saline solution is a bit higher, even 100 kilo ohms. And finally, the dry electrodes have the least amount of contact, so also the highest target impedance, between 500 to 2,500 kilo ohms. But this is not all, only the conductive material, also the skin plays a role. And there are basically various kinds of skins. First, if you have exposed skin, like if also or bald people, that's actually not the best for EEG, because exposed skin without much hair tends to harden a little bit. I mean, it's good for the person that your skin is not sensitive, but for EEG it's not perfect. For protected skin with some hair, it's around 120 kilo ohms. There are different ways to reduce it. You can remove the grease also. For example, just tell your participants to wash their hair before. But you can also apply some rubbing alcohol before the measurement to scrub away some of this fatty skin oils to reduce it around 2/3. In certain cases, you can also abrade with a abrasive gel or blunted needle, but this is not always needed. On the other hand, if people have too many, if they have a lot of hair, it's also not ideal because you need more gel. So basically, if you are a man suffering from balding, you can also say, I'm just optimizing for EEG, because that's actually the perfect hair. You need some hair, but not no hair and not a lot of hair. You need some hair to have the best EEG signal. And again, there can be different gels. You can have clear gel, which is only conductive. You can have abrasive gel, which is conductive and abrasive. It can be very liquid, or it can be viscous. It can also be salty or free of salt. And there are different purposes for that. Active electrodes use only clear gel, so you can get away with higher impedances and don't need much abrasion. Passive electrodes usually have abrasive gel and some additional manual abrasion. Liquid versus viscous basically depends on how many EEG channels you have. If you have a low channel count, you can get away with medium viscosity, so it flows easier to the surface of the head. But if you have a high channel count, the electrodes tend to be very close to each other, so you don't want them to be connected with a gel bridge. So you need a high viscosity EEG gel. And salt versus salt-free is also depends on your use case. So the skin, generally, depending on what people did, if they have moved before, did some sports or just sat around, it's around 0.9% salt content. And the salty electrode gel has a much higher salt content, between 3 to 10%. This leads to the gel being self-improving over time, because the salt or the high salt content from the gel mixes with the low salt content from the skin, so the impedance improves over time. If you prepare an electrode and don't have immediately good impedance, you don't have to keep continuing only on this one electrode. You might just go to the next one, and once you come back to this electrode, it might have already improved. If you want to measure these very slow potentials of 3 Hertz or below, this is only possible with salt. But on the other hand, salt can be unpleasant if you have sensitive populations, for example, with kids or babies even, or if you're dealing with abraded skin, then salt can literally rub salt in the wound, which some people might not be very positive to do. Okay, I talked a whole bunch about electrode impedance, but the other factor I didn't mention yet is once it passed through all the electrode impedance and through the electrode cable, there's another part to impedance, which is precisely what I mentioned before, the amplifier input impedance. And these two depend on each other regarding the signal quality, because best signal can be done, for one, if you prepare your electrode, so you have a low electrode impedance, but also if you have a high amplifier input impedance. And to give you some example values, what this amplifier input impedance is, the ActiveChamp Plus has over 1000 mega ohms. The BrainAmp standard has 10 mega ohms, while the BrainAmp DC and MR Plus can switch between 10 mega ohms and 10 giga ohms. And the LiveAmp has above 200 mega ohms. So several orders of magnitude higher than these target impedance levels I talked about earlier. And this is important because also this committee report from Kyle and colleagues mentioned the electrode impedance is less important than the relationship between electrode impedance on the one hand and amplifier input impedance on the other hand. And this is precisely why we don't pierce the skin anymore, because the modern amplifiers all have such a high input impedance that we can basically get away with a relatively high electrode impedance. So we don't have to hurt our participants anymore, because our amplifiers are good enough to record good quality signals with medium impedance levels. One additional input impedance I want to mention here, is the ActiCap, which is a special type of electrode. Paulo will also talk about it later, when to use it. But basically, I want to mention here that if you use the active electrodes, you basically have an input impedance already at the electrode level, not at the amplifier level. And this can improve your signal dramatically in some cases, depending on your environment. In short, you don't only have the signals from these passive electrodes directly on the brain, or not directly on the brain, directly on the skull, but the electrode cable can also play a role, which you usually don't want. So if you have a passive electrode and a long, maybe even coiled up cable, this can act some sort of as an antenna to record all environmental noise as well. So in this room, we have a lot of lights and electricity, which would all be picked up by the electrode cable as well. So we have cable noise. And the active electrode is one way to solve this, because you have an impedance conversion already at the electrode itself. So the electrode cable is kind of shielded against external influence and is more immune to environmental noise. On the other hand, the active electrode also has a little LED in it, so it lights up and tells you how good or bad the impedance is, which also makes your preparation easier. In short, you can get a better signal even with bad impedances and with higher environmental noise. But there are a bunch of other specifications as well. So for example, the maximum number of channels. So I showed you this huge box of 2-channel EEG from the 50s, but now we are 160 or sometimes even 256 channels, which is basically how many channels we can fit on the head, and vice versa, which tells us how good can we locate where the signal comes from. And the basic idea here is the 1020 system. And for that, I make me a little bit bigger. Hello. The 1020 system basically uses anatomical landmarks we all should have on our heads. One is the nasion, so it's not the nose itself, but it's basically the little dent here on top of the nose. The other is regarding the ears, but it's usually not the ear itself, but the pre-auricular point, so before the ears, both right and left. And the last one is the back of the head, the inion, that I can't show you as easily, but basically if you go back on the back of your skull, you feel a little dent where basically the skull ends. For me, it's around here. The skull ends, and this is another point you can use to pinpoint locations. And the 1020 system basically connects these points, like you imagine that there's a connection between them, and then divides them into equal sized segments. One is, for example, 10, because that's why 1020, 10% of the length from here to here is the first one, and this constitutes the headline. So people don't use that many heads maybe anymore as maybe they did 100 years ago, but if you would wear a head, it would be roughly this line where the head ends. And this is 10%, but then you move an additional 20% for the next sensor and so on. I'll make myself small again so you can see the example pictures. So this 1020 system basically divides this into equal sized segments, and the whole idea here is that you have equidistant positions. Every head will be a bit different, but you still want basically a relative same positioning of your electrodes to reach general conclusions. The problem with the 1020 system, or not problem, but the trade-off with the 1020 system is it has 21 channels. But our digital amplifiers usually like to talk in powers of 2. So most of our amplifiers have, for example, 16, or most of them rather start at 32 channels. And with 32 channels, you are kind of in between, because you can also fill up the 1020 system with a 1010 system. So you don't have 20% difference between the positions, but 10%. Basically, at each each middle of the line, you have additional sensor. But these, again, don't fit 100% into 32 channels. So the 32-channel system usually has a trade-off of all 1020 positions and some of the 1010 positions. And if you go one step further, the 64 channels has more of the 1010 system, still not all of them. You can basically see they usually fill up from the center of the head, because this is usually the most interesting point. And regarding the question earlier, in this case, the reference electrode is positioned here. So this is basically where all electrodes are referenced to, but this can be on another position. We will talk about the position of reference electrodes later. And the last one I want to show you is also basically most expensive or expansive and expensive system is the 256 channel count, which is then the 10-5 system. So we basically divide this into 5% segments, which fills in a lot of positions. So to sum up the different channels, many different caps exist. You have active, passive, you have gel, wet, and dry sensors, high, low channel count. There are also special caps for special environments for MR, MEG, or TMS, or sleep. Some have a fixed electrode, a reference electrode. Some have a variable reference electrode. For some, the electrode positions are fixed. For some, you can also remove them. And they also come in all different sizes, so adult and children sizes, but also all sizes in between. Different head shapes. So we have an oval cuts or round cuts. It kind of depends on different regions of the world, where on average people have slightly different head shapes. Different fabrics, so they can be high precision or high comfort, which is also kind of a trade-off you have to choose. And some of them even have auxiliary sensors built in for eye activity, muscle activity, heart activity. And there's basically no perfect kit for everything. There's always a trade-off between signal quality, ease of use, and preparation time. And Paolo will later talk you through which to choose in which situation. But going through our list, we also have these resolution specifications, which, for example, in this case tells us 2 to the power of 24 bit equals roughly 0.04883 microvolt per bit, or different hertz, for example, 100 kilohertz. And this is basically the effect of having a digital representation and not a paper representation, how fine the digital grid is. And we'll show you this in more detail now. So if you look at in a digital amplifier or modern amplifier, we have at least 3 steps. So first, we have the differential amplifier that, as I mentioned, mainly amplifies the difference between at least 2 sensors. You always need a reference and a signal electrode, and what you then record is there's no electricity at any point. There's always only a difference between at least 2 points, and you only look at the difference of the electricity between 2 or more points. And this gets then not recorded on a piece of paper anymore, but converted with an analog to digital converter, or ADC, that converts this raw signal to a binary representation that can be analyzed with algorithms and analyzer and so on later. And the idea here is this ADC is a crucial point, because this basically records the continuous signal at regular time intervals. And you can think about this in 2 dimensions. One is the X dimension. In this case, I chose a sine wave, where you basically can see the sine wave going from 0 to 1 to 0 to -1 to 0 again over an arbitrary 2 time points. And this amplitude then gets recorded at different time intervals, for example, at 0.4 or at 0.2. And if you have 0.4, you can imagine, if you connect these dots, you have a representation of the original sine wave, but it looks a bit janky because you don't have many points. You still have enough points to represent the signal, but you see it's a bit rough on the edges. While on the 0.2 time resolution, it gets a bit smoother already because you have double the time resolution. So the sine wave is more accurately represented. And this basically depends on your frequency of the signal of interest. The recommended sampling rate is at least 5 to 10 times the frequency of the signal of interest. And then one example would be that event-related potentials usually happen between 1 to 50 hertz. So if you multiply this by 5 or 10, you arrive at the recommended sampling rate of at least 250 to 500 hertz. And this is also what I showed here. So this sine wave is represented with a 5-time sampling rate here on the left, and then with a 10-time sampling rate on the right, to give you an example. But you don't only have the grid in the x-axis, you also have it in the y-axis, which is the amplitude, and that's where the resolution comes in. And this is the bits per volt, and the higher the bits per volt, the higher the amplitude resolution, and this kind of depends on the strength of your signal of interest. And if you go back to the sine wave again, you can also imagine to divide up the y-axis in different segments. So here we have the 0.4 amplitude resolution. So you have this blocky design, also representing the sine wave more or less. And here, with a double the resolution, these steps basically become smaller and smaller. It's still, of course, rectangular. It's not an analog perfect sine wave, but it approximates the sine wave to a higher degree. And the steps here are determined by the bit depth of the amplifier, which is literally the number of possible steps you can have. So how many of these lines can you fit or can you record in the amplifier? The brain amp, for example, is a 16-bit amplifier, which means it has 2 to the power of 16 possible steps, which is roughly 65,000. While the EEG is a 24-bit amplifier, which means 2 to the power of 24, is around 16 million or 17 million possible steps. But it's not only the steps or the number of steps that play a role, but also how they are distributed over the measurement range, because the bit depth and the amplitude resolution together determine the measurement range. One example calculation is here. The brain amp has a 0.1 microvolt per bit resolution, which means you have 6,500 microvolt possible values, because you have to basically shift this 65,000 by 1 decimal point, and then divide this up to equal size segments, positive and negative values. So it goes from minus 3,000 to plus 3,000 microvolt, or from minus 3 to plus 3 millivolt. And if you take both the amplitude resolution and the time resolution together, we arrive at the grid size I mentioned earlier. So, for example, we have the ground truth, the perfect smooth sine wave again, the top left, and the 0.4 time resolution here in the middle, and the 0.2 time resolution on the right, and similarly the 0.4 amplitude resolution in the middle, and the 0.2 amplitude resolution at the bottom. And if we combine both the bad time and the bad amplitude resolution, we arrive at this segment, and you have basically this grid size, and the points where these meet are the only values you can record. And because you don't have that many available, your sine wave ends up looking like this. While if you have double the grid size available, I can point with a finger here, you have a much smoother sine wave. Still, it's not perfectly smooth. It's still crooked a little bit, but it's a better representation because basically your grid size is smaller. And then you can also, of course, say, then I'd take a basically almost infinite resolution. Why don't I go up to the maximum amount I can? For example, the EEG can sample up to 100,000 hertz. That's much better than using 1,000 hertz, right? That is true, but that is also basically diminishing returns. So the file size might increase exponentially, but your signal only gets marginally better because not only is your signal better represented, but you also need more hardware space, and in the end, for analyzing, also more RAM space, which AI companies are just now buying all up. So there's not much RAM available. There's still enough RAM available, of course, for good signal analysis, but you don't have infinite RAM on your PCs. So your analysis might take longer, or in the most extreme case, your system might even crash because it can't handle the amount of data if you have a very high resolution. Vice versa, what happens if the resolution is too low? And this is another specification I want to highlight here, which is the bandwidth of the EEG channels and the input voltage range. So this example says you can record up to 7,500 hertz and plus minus 400 millivolt. And if we again look at the X and Y, the clipping from the measurement range is relatively easily explained. It's basically just how positive or negative signals, what's the maximum positive and maximum negative value you can record. And if that's not sufficient, you can literally be cut off. So if you have a sine wave, as shown here, and your measurement range ends here and here, basically the peaks and troughs, the most extreme peaks and troughs are not represented because they're outside your measurement range. This is in practice only an problem usually with a 16-bit amplifiers, for example, the brain amp. But for the brain amp, you can also switch the resolution to account for this. So the brain amp 0.1 microvolt resolution equals in a plus minus 3 millivolt measurement range, but you can switch it around and basically have 5 times worse resolution and 5 times higher measurement range. If you use a 0.5 microvolt resolution, you end up with 16 millivolt measurement range. Yeah, that's the y-axis. but it's a bit more complicated if you talk about insufficient resolution over time. And one analogy I want to highlight here is taking a picture. Because if you take a picture of a very high spatial resolution image, for example, this brick wall where you have little or very small bricks, which is basically a high frequency, spatial frequency, it looks like this. Hopefully it looks, because Shiva mentioned it's blurry for some people, it might already look bad if your resolution at home is bad, but for the ones who blown up their screen, it might look better. So this should be a more or less well-resolved brick wall. But if you have less pixels available, these artificial lines might emerge that are not in the brick wall, but are basically just a result of not having enough pixels to represent all of the bricks individually. It's also called a moire pattern. And this is kind of the aliasing we are afraid of. If you now take this into the EEG realm, you can also think about, for example, an analyzer here. I recorded just line noise. So this is a 50 Hertz noise. You can already see it's not perfectly resolved, so it's not perfect sine wave, but a little bit janky. But now what happens if I decrease the, or if I zoom out, basically? Hopefully that happens. Yes. So if I zoom out, you see first, okay, it gets squished together, but depending on your screen, you might see some flickering at certain points, that artificial patterns emerge and disappear again. This is even more the case if I would, or if you now decrease the size of the window, you might see some flickering here that basically goes higher frequency, lower frequency, and higher frequency again. It's a bit hard to say when you will see it because it depends on your resolution at home. But for me, now there was a time where it got in and out, now again, in and out, now it flickers more. And basically, the lower the pixels are, the lower the frequency I see here are as well. So now there was a short period where I saw a slow oscillation. And the oscillation you see here will be slower and slower the smaller the picture is. Now another small oscillation comes in. Now, for example, you see for a brief moment a very short oscillation, for a short moment a low oscillation that then gets high again. And this is basically what happens if you don't have enough resolution. So the definition of aliasing is when different signals become indistinguishable or aliases of one another when sampled at an insufficient sampling rate. Again, going with sine waves, because sine waves are just the perfect example, we have a sine wave increasing in frequency here, and the sampling points being sampled at with these dots. Two things happen. At first, the original sampling and the reconstructed frequency are the same until a certain breakpoint where the reconstructed frequency will get lower while the real frequency will get higher. So now you see this getting higher while this reconstructed frequency getting lower. And if I stop this at a moment, you can also see why this happens. So if I now have a high frequency sine wave and my sampling points spaced in between here like so, if you connect these sine waves, these sampling points, you arrive at this very low artificial sine wave, which is not in the real data, but just an artifact from having insufficient sampling points for the frequency. And the solution for that is usually an anti-aliasing filter, which is built into the amplifier. So here I simulated a chirp, which is basically an increasing frequency. You have a low sine wave here, then basically each sine wave gets a higher frequency from 1 to 20 Hertz. So it gets higher and higher and higher in blue. Then in orange, you see the reconstructed frequency with the sampling points. Each of these gray lines is one sampling point. And while it's not a perfect representation in the first half, you might lose some here. For example, some of the peaks are cut off. It's still the correct frequency. So this wave is not appearing at a different frequency. It's just cutting off some of the top here. But at this Nyquist frequency, which is half here at the half point, you see that the reconstructed sample points are much slower than the real frequency is. But here on the bottom, you see the solution, which basically employs a filter. We talked about filter earlier, and we will talk about filters also on day 3. But in short, this anti-aliasing filter filters out the high frequency signals that cannot be sampled. So the reconstructed frequencies only show you the real signal and don't show you any of the aliasing artifacts. And yeah, I think I skipped the animation here because I want to show you Now the last examples with real frequencies, or not real frequencies, but frequencies more in the range of real EEG signals. So before I showed you very slow frequencies with unreasonably low sampling rates, but now I showed you a 10,000 hertz, 2,000 hertz, 400 hertz, and 200 hertz sampling rate, and a chirp, so a frequency from 0 to 200 hertz. This is more like the range of real EEG signals. Very rarely do you look at frequencies over 100 hertz, but it's theoretically possible. But these are also sampling rates you can choose in most of your amplifiers. And you can see, if I zoom in here a little bit, that at the top right, this is literally this 10-time frequency, or 10 times the sampling rate than the frequency of interest. So the frequency goes up to 200 hertz and the sampling rate is 2000 hertz. So it's perfectly, or almost perfectly reconstructed. You lose some of these peaks, but it's relatively well preserved. While if you use a sampling rate that's theoretically still enough, a 400 hertz sampling rate, you don't have any aliasing signals here, but you have lost a lot of frequency. For example, here around 190 hertz, you lose a lot of your peak frequency. You have the correct frequency still represented, but you lose a lot of it. While if you use a 200 hertz sampling rate, then yeah, the second half is basically wrong. This is all aliasing artifacts. So the Nyquist frequency is the theoretical maximum where you can still represent the signal. But in practice, you should only consider frequencies considerably lower than the Nyquist frequency. So again, the 5 to 10 times the sampling rate of your signal of interest. Yes, and the anti-aliasing filters we have in our amplifiers are usually around 1/4 the sampling rate. So you can look at it in the specifications of the individual amplifiers, but that's a rough rule of thumb. They are usually at 1/4 or sometimes even lower, specifically for the brain amp, which is also purposefully built to survive very hostile conditions with the being recorded in MR. We have the option to use a 250 hertz filter in the brain amp with a resolution of 5000 hertz. So this is what I plotted here. So theoretically, with a 5000 hertz sampling rate, you could resolve up to 2500 hertz signals, but the anti-aliasing filter cuts off basically almost all of it. And you only have this very low frequencies at the very left, because this filter cuts out so much, so you don't have any lost signals or basically not misrepresented, but underrepresented frequencies. Yes, and these filters are also in 2 stages of the signal chain. What I talked now about is all the filters in the hardware. So this low pass or high cutoff filter, filtering out all high frequencies that cannot be represented by your ADC. And this is always there and always necessary in every ADC, but there are a lot of other filter stages which are optional. So some amplifiers, for example, the brain amp, can also cut off low frequencies, but that's not always needed. And importantly, these are usually the filters you are dealing with if you record EEG signals. So you can select filters in your software, for example, to change the way it's displayed on your screen, so you can monitor your signal better. You don't want to see line noise, for example, so you filter out line noise. But importantly, this only filters out the signal after it's been converted, because we get a lot of questions, people saying, what filters should I use in my software? It doesn't matter for the safety of the data, basically. The hardware takes care of anti-aliasing artifacts already before the ADC happens, and this happens automatically, or rather, even if you choose the wrong hardware filter settings in the brain amp, there's always a safety setting that you, before it's downsampled to the sampling rate you want to see it, there's an additional anti-aliasing filter. So these are usually not user modifiable. These are, but they don't save you from aliasing. The hardware design automatically saves you from aliasing. For completeness, if you would stream your data to another software with remote data access, the software filters are also skipped, but the hardware filters are still in. To give you some example values here, the ActiveChamp, for example, has an 8 kilohertz low-pass filter and no high-pass filter, and sampling rates between 10, 50, or 100 kilohertz. On the other end of the spectrum, the LiveAmp has a relatively lower sampling rate of 1,000, 500, or 250 hertz, and then the anti-aliasing filters are around 1/4 of that, 262, 131, or 65 hertz. One of the last specifications I want to talk about is common mode rejection. In this case, it's 100 decibels, which of those of you who know decibels, it's a logarithmic scale, so it's a very high value. And in short, this is basically the higher signal quality. I want to briefly explain common mode rejection. So a differential amplifier uses at least a signal electrode and a reference electrode, but most of them should also use a ground electrode to basically center your measurement around a neutral ground. And then the difference between signal versus reference gets recorded and amplified. And common mode signals are attenuated in various ways. And common mode signals are basically signals that are both present in signal and reference electrodes. They are identical also in the phase and in the strength across signals. And the common mode rejection, or sometimes also called common mode rejection ratio, is attenuation of this common mode noise. In some amplifiers, you also have the option to increase the common mode rejection basically with an additional active shielding. This is an option for the ActiChamp and the ActiCap control box, and it sometimes can improve the common mode rejection. And channel 1 in module 1 is used at the source. That's not that important, other than that if you use active shielding, you should not only prepare your ground and reference very well, but also the channel 1 in module 1 very well, because this is where the active shielding comes in. And the common mode rejection basically removes signals that's all the same in all channels. So if you imagine you have 4 channels all showing the same sine wave at the same time, the common mode rejection flattens all these 3 signals. But if you would have non-common mode, so for example, 3 channels showing the sine wave and the 4th channel being quiet, if you enable active shielding, this would flip your noise around and re-inject it into the previously quiet channel. One metaphor for that would be noise cancelling headphones some of you might have. So if you have noise cancelling headphones in an environment where you have a very stable, very samey background noise, for example, in a car, train, or plane, where you have just this background hum, this can be very well reduced by enabling your noise cancellation feature in the headphones. But if you enable noise cancellation in a very quiet room, you might then start hearing noise that wasn't there before because the room is already quiet. So basically, don't use it if you have a good signal, only use it if you have a lot of same signals in all channels. The noise depends on the source. So power lines, computers, displays, wireless equipment should be present in all channels and similar in all channels. And the more similar it is, the better it works. But it can also overcompensate. So in short, if you want to use it, first check if it really makes your signal better. Also check if you can eliminate the noise at the source. And if you're still not sure, when in doubt, don't use active shielding. Last specification I want to highlight is trigger input and auxiliary channels, because we usually want to combine our EEG recording with other signals as well. So to briefly show this, at the very basic level, you have the EEG, signal, reference, ground going to the EEG amplifier, recorded on the software. But you want to usually combine it also with a stimulation, and the stimulation should send triggers into the recording hardware. For example, if you show a stimulus A and B, or if people react with A and B, this also goes into the EEG amplifier. And additionally, you might want to record peripheral physiology, for example, heart activity or breathing, that also goes into the amplifier. And this is basically the auxiliary channels, and the other is the trigger channels. So all together go into the EEG amplifier, then get recorded, and then get analyzed. So to sum up, what do these specifications mean? So the input impedance and input noise, we have a high input impedance and a very low input noise, which allows us to not torture our participants anymore, because they are good enough already with higher impedance electrodes. The high channel count of, for example, 160 EEG electrodes means we can precisely locate the signal. The 24-bit digitization and 0.04 microvolt per bit means we have a very low digital grid size. The input voltage range means we can record very large signals. The bandwidth up to 7,400 Hertz means we can record very fast signals. The common mode rejection means we can have a higher signal quality, reducing similar noise in all channels. The aux means we can expand with peripheral physiological devices. And lastly, the trigger input means we can combine it with other devices. And with that, we might have time for 1 or 2 questions. I had 3, but I think we only maybe have time for 1 or 2. But Shiva, I think you're best to judge. Yes. So CMR, I just mentioned. How does CMR help improve EEG signal quality? Is it common mode rejection reduces shared noise signals? Is it clear motion rate preventing signal aliasing? Is it colossal magnetoresistance reducing impedance? Or is it Giles-Matcher representations separating signal sources? All 4 effects are actually true. If you look up CMR in Wikipedia, all 4 show up, but only 1 is important for EEG. I already see this question might have been too easy. But it's good that you all paid attention, at least everyone that clicked. Yes, CMR in the EEG sense, at least, it's the common mode rejection, reducing the shared noise signals. Do we have time for 1 more question, Shiva? Yes. And that is, what does not bridge the electrical gap between EEG electrode and the scalp? Is it electrode gel? Is it saline solution? Is it the oil deposit? Or is it dry skin contact? So 3 out of 4 are real EEG sensors or the stuff EEG sensors use to bridge or connect to the skin. And 1 of them you should avoid. Most of you are correct that oil deposits, so if you have oily, greasy skin or hair, this is something you should remove before the EEG recording starts. But all the other 3, electrode gel, saline solution, and dry skin contact, are all real EEG electrode types. Dry skin contact, where the most of you clicked, is technically the worst signal quality because you have the least amount of connection, but it can still work in certain situations. And I believe Paolo will tell you in which of those and why you should, or in which situations you should use dry skin contact. Then one more quiz. If F is the EEG frequency of interest for your planned analysis, the recommended sampling rate for your recording should be half F, F, 2F, 10F, or 200F. So for example, if you want to record 10 Hertz alpha waves, should you use a 5 Hertz sampling rate, a 10 Hertz sampling rate, a 20 Hertz sampling rate, 100 Hertz sampling rate, or 2000 Hertz sampling rate? Most of you are correct. The at least recommended sampling rate should be 5 to 10 times as high. So 10F in this case would be correct. Technically, 200F you can still get away with if you really want a lot of data, but usually it's enough to sample at 10F. Half F is not correct. You would not be able, so for example, if you want to record 10 Hertz signals and would have a sampling rate at 5 Hertz, you would not be able to accurately recreate a 10 Hertz signal from a 5 Hertz sampling rate.
Now the idea is to try to find the best technology and relate these characteristics that David mentioned to our research and how to define the best technology for our research. And so when we are trying to get the signal from the brain, we first detect the signal with the electrodes, and we have a few electrode technologies to discuss. And then we have the amplifiers, which will amplify and digitize this signal. And we need to discuss this combination of electrodes and amplifiers for our research. So first, let's take a closer look at the electrodes and the options that we have there. What's common to all electrode technologies is that they are going to be the first step to detect this signal coming from the brain. And actually, we detect signal that reaches the scalp. So we have the electrical activity coming from the brain, and the summed effect, as mentioned in the previous talks, reaches the scalp, and we want to detect it with our electrode, which will be positioned all over the scalp. And to get the signal, there is going to be an opposition to it. And since this is an alternating current, this is called impedance. and we want to minimize the impedance to have the best connection between the electrode and the scalp to get the best signal. Related to how electrodes handle this connection and contact with the skin, there are a few characteristics that we can discuss and try to group different electrodes. We are going to exemplify these characteristics with the electrodes that we have available from Ring Products and our partners. So one aspect is if the electrode has an active circuit or if it's a passive electrode. And the other aspect is what is the conductive medium? So how is the contact between the electrode and the scalp established? So the most traditional electrodes are passive gel-based. So this does not have any circuitry on the electrode, and it makes the connection with the scalp via gel. Alternatively, the passive electrodes can also have the variation of making the contact with the scalp via a saline solution with a sponge that's soaked in the saline solution. Another example would be the active gel-based electrodes. So they would have the impedance conversion on the electrodes, as David mentioned, and it would still use the gel to make the contact between the electrode and the skin. Another example would be electrodes that directly make contact with the skin, and these are dry electrodes. They don't need any gel or saline solution. And this is usually more common with active electrodes because the impedances, as we're going to discuss, are going to be higher, so it makes more sense to use an active electrode technology. And there are different variations of these types of dry electrodes as well. So focusing on the options that we offer in Ring Products as examples, as they cover a wide range of possibilities and will exemplify very well the technologies available. We have basically the gel-based, which is more common, related to abrasive or viscous gels, passive or active electrodes. And then we have the options of sponge-based solution and the dry electrodes. This is the more common grouping of these electrode technologies. And now we are going to discuss a little bit the characteristics that are affected by this kind of technologies, the differences. So first, we want to get more signal, usually, and reduce noise. And usually gel-based technologies will have an advantage on that end because they establish a better contact between the electrode and the scalp. And also with gel-based solutions, you can have longer measurements in general. But there are other characteristics that we have to consider depending on the research that you want to do and also our participants. So we have to take into account the comfort of the participants, which can be increased in saline solutions. Also think in other aspects like the easiness to clean the hair or to switch from one participant to the other or to prepare the participant for our experiments. So we want to optimize our setup. So all of these characteristics have to be taken into account to decide the technology. So I'm going to discuss a little bit how the technical characteristics of these electrodes now relates to these aspects that we want to optimize in our research. So for example, you already saw this image, but the different electrode technologies, different electrode types will have different target impedances. And the impedance level will be related to the signal quality or detecting less environmental noise and more the signal of interest coming from the scalp. So usually with the passive gel-based electrodes, you have very low, you can have very low target impedances. With active electrodes, you can work with higher impedances because they have the impedance conversion on the electrodes. When you use saline solution electrodes, usually we work with impedances in the range of 60 to 100 kilo ohms. And then when we are using dry electrodes with direct skin contact, then it can range from 500 to 2500, depending on the exact electrode that you're going to use. But this is related to signal quality overall and to the preparation time. So if you don't need to prepare to get the impedance as so low, then you can get the preparation time faster. So you can see that there is an opposite relationship between the target impedance and the preparation times in these electrode technologies, with the dry and saline solutions being the fastest. And then when you have to apply the gel on each electrode, this can take a little bit of time, depending on the type of gel that you use. And the other aspect we have to consider in sequence when you're talking about using gels or the type of electrode that you're using is the possible measurement duration. So the gel has a big advantage of allowing you to establish the good contact between the electrode and the scalp for a long period. So you can have 8+ hours of recording with gel-based solutions. This will depend on the viscosity of the gel. And on the other hand, if you go to saline solution, what can happen if the experiment is longer is the sponges could dry up during the experiment, and you would need, for example, a break to get them wet again. Or if you are working with the dry solutions that you have a direct contact with the skin, this depends on pressure to maintain the contact between the electrode and the skin. So this pressure over time can be discomfortable if it's a long period. So usually this is recommended for shorter experiments. And these previous aspects that we discussed result in the comfort or the participant experience. So it takes into account the comfort wearing the system, the comfort preparing the cap, the comfort cleaning up after using the EEG system. So in that combination of factors, the saline solution, the RNETs that we offer, would be the most comfortable for the participant, as they would have a combination of fast preparation, low level of residuals on the hair, and an easy cleanup for the participant and comfortable to wear. While the dry electrode solutions would be fast set up, they can, if the experiment is longer, they can become uncomfortable. And the active gel-based solution, for example, is an in-between, as it requires gel, so it has residuals on the hair, but the cap itself is pretty comfortable to use for a longer time. And abrasive gel would require a little bit of abrasion to prepare the electrodes, so and longer and leave more residuals and longer preparation time. So in that sense, it would be less comfortable. So again, discussing the residuals and cleanup, we have both the aspect of the participant that we cover a little bit of the residuals that are left, but also the easiness to clean the system as well. So in practical terms, when you're doing research, you have to plan the time you need to prepare the equipment and also to clean up the equipment after the experiment to switch for the next participant. In this sense, the dry electrodes can be easily cleaned directly, because you don't have to deal with the residuals of the gel as well on the electrode side to clean them up. And the saline solution similarly is they are easy to wash. You just get them wet with the cleaning solution, which would be basically water and a shampoo. And with gel, you need then to have a more careful cleaning of each of the electrodes to remove the gel residuals. So the thicker the gel, the longer it takes to clean the system as well. It takes more time for the participant to clean it from their hair. So comparing again the different technologies, we see that we have more signal and less noise in general, and longer experiment durations with gel-based solutions. And we have more comfortable with saline solution. We have a fast preparation and clean hair, low residuals with both saline and dry electrodes. And we have a very quick transition to the next participant or cleanup when using the dry electrodes. But I'm going to discuss a little bit what we can do in each of these cases related to the signal quality or having less noise, the comfort experience for the participants, the preparation, and the transition to the next volunteer. We have some options there, so this might not be such a linear line as presented in the previous slides. So to deal with noise, as previously mentioned, this is not only dependent on the electrode impedance, but also on the amplifier input impedance. So it depends on the relationship between both. So having amplifiers with high input impedance is very helpful in this sense. And the second thing would be, indeed, the active electrodes have an advantage to pick less noise. And this idea is because in a usual electrode, you would be more sensitive to noise being picked up as an antenna effect on the cables. While when you have the active electrodes and have the impedance conversion directly on the electrode, we avoid this antenna effect of the cables. So this, as you've seen before, we have an active impedance conversion on the electrodes that is very helpful for the signal quality and allows us to get good signal with high impedances. Then the other aspect is that for some technologies, it makes sense to have the electrodes and cables shielded, especially when you work with dry electrodes. This can be a positive option to deal with the noise as you have higher impedance level. But another aspect is that aside from having active technologies, proper routing of the cables and fixing them also allows to reduce these artifacts that would come from motion of the cables. So proper routing or having straps to fix the cables can be very helpful. Regarding the fast setup, we can consider that, again, if the system allows us to work at high impedances, as for example the active technologies, we can prepare the system faster. Aside from that, we have practical aspects when using the systems. So basically, when you're preparing the participant, you're going to be checking the impedance levels on your electrodes, and the way this is presented to you can make the preparation easier. For example, if you have an LED that shows the impedance level, if it's bad in red, or changes colors progressively to a green tone when the impedance level is good, this can make the impedance very practical. And this is one advantage of the active electrode technologies can offer this as well. Since you have a circuit there, you can have this kind of feedback on the electrode. Regarding comfort of the participant, again, if we can work with higher impedances, we don't need to have abrasion on the skin, and this will be a more comfortable experience for the participant. And specifically when you consider the electrodes that make direct contact with the participant, then the shape of the electrodes makes a difference. So instead of having a single connection point between the electrode and the scalp, if you spread this pressure point in several points of contact, then this is more comfortable. You have less pressure. Regarding the quickness to clean up and transition, here one important aspect is that if you have one system with one cap, one electrode, you have some limitations, because if you want to transition, then you have to clean that electrode set, that cap, and to be able to prepare the next volunteer. Aside from that aspect, you also have to consider that your participants will have different head sizes. So depending on the cap that your system uses or your headset, you have to check what size range it covers. So you might need more caps to cover a certain size range for your experiment. But the idea is that if you can have more caps of that system, then this helps with the transition, even if the system by itself, by a single cap, would not would take some time to clean, to then prepare the next participants. If you have several, you have an option to deal with that as well. Good. Now that we discussed a little bit the characteristics of the electrodes related to the point of interest that we want to optimize in our research, let's focus on some specific research aspects and when each of these previous points is more relevant. So, for example, depending on the requirements we have on our data analysis, this can affect our decision of electrodes, the best electrodes. Let's say, is our analysis quite simple, straightforward, in the sense that it's a traditional analysis with a strong effect, and we have a lot of trials to make an average. For example, when you're doing an event-related potential, the more trials you have, the more that you're going to filter out the noise by doing this average. Another example of a pretty straightforward traditional analysis would be a frequency analysis in the range of 1 to 45 hertz, for example, with a Fourier analysis. And for these more traditional cases in this frequency range, then we would be able to work with higher impedances, because if we have more trials, we can make a longer experiment and compensate for this noise. By averaging it, it's okay to have a higher impedance. Also, in that sense, we will have the option to work with gel-free or sponge-based solutions, which can have a limited range because of this high impedance as well. And we can then have the advantage of having a quick setup to prepare our experiments, and this can give us the possibility of having more volunteers and more trials. So this compensates overall for the maybe getting more noise with this kind of technologies. So, for example, these would be good examples for the RNets or for the dry electrode systems that we have for the quick CJAC systems or the Express. But however, if we have an analysis goal that's more complex, or the effect that we want to identify is more subtle, or we don't have that many participants trials, then we need to prioritize other aspects. So for time frequency analysis, as Michael already discussed a little bit, or connectivity analysis, it may be necessary that you go for lower or higher frequencies, and also your signal to noise ratio will need to improve. In that sense, if all of some of these questions we reply yes to, then it's more recommended to use gel-based electrodes, and then it makes more sense to really take careful time and preparation to lower these impedances. For example, these would be good applications for either the active gel-based electrodes or for the passive gel-based electrodes. And other types of analysis that would impose requirements on the electrode side would be, for example, source analysis or independent component analysis that we want to extract from our data. Or even, depending on the type, if we want to use an average reference option for analysis, these would all require more channels, so a higher coverage of our head. And a minimum recommendation would be, for example, 64 channels in these kinds of analysis. Once you have more channels to prepare, then it also makes sense to consider setups that are quicker to prepare. So the balance of the sponge-based solution can be a good trade-off depending on the analysis that you're going to do, with still providing a quick preparation and good quality for that kind of analysis with a high channel density. And it can cover the whole head as an X-sphere, which is helpful for source analysis. On the other hand, it also can be a good option to have the active gel-based electrodes, because this can take a while to prepare, but they don't take that long, and they provide a great signal to noise ratio. So again, depending on the analysis, it makes more sense to have dedicate a bit of time in the preparation to have the best signal. And we have an option that's the cap track that can be used depending on the source analysis that we want to do. We can quickly scan the position of the electrodes to have a very precise information of the position of the electrodes for their source analysis. And yeah, we have a lot of material related to how to best optimize the setup, so you can prepare these electrodes in a quick way in our YouTube channel. Good. Aside from the data analysis aspect, we also have the aspect of the needs from the participants. So, are we working with a sensitive population? Sometimes the population can be too sensitive to the gel processing or application processing, especially if we use abrasive gel. So in that case, the highest comfort and quickest setup would be recommended. So again, the sponge-based solutions like the RNet would be very helpful on special populations. For example, the infant studies, they are very suitable for the RNets, as they are very comfortable for the babies, and then can cover a wide range of sizes and easily adjust to be more comfortable with the straps. And they don't use syringes, so we don't just get the electrodes soaked in the saline solution and eventually use the pipettes to get a little bit more dry each electrode if needed. So this is a good option, but also we can have a great signal to noise ratio again when using active gel-based electrodes. And these are also comfortable to be used with infants and could be a good alternative, though they will require a bit of a few minutes to prepare the cap longer than the saline solution option. Another aspect is considering the time your participants have, and this is both for the time that your participant will spend doing your task, but you have to consider the time that the participant will need to clean up afterwards. So if the participant comes for experiments and you apply the gel, the participant needs to have the time to then clean up, to then go to his next activity, his or her next activity. So considering the limited time, we may focus on gel-free systems. For example, the dry electrodes from CGX, which would be allow you to do the research with no residuals for the participants and very quick to prepare. If moist hair is not a problem for the participants, also the sponge-based solution is very useful and a good balance between comfort and signal quality. And the other aspect is if we plan to have several participants in a row. So when you want to have a quick transition between one participant and the next, first we need to cover the different head sizes and then consider the cleanup between the system to the next one. So either we need a system that covers easily different head sizes. One option is having electrodes that can be attached to different caps with different head sizes. So this is an option also with the active electrodes that we offer. They can be snapped in and out of the caps. So you can, with one electrode set, change from between different head sizes. But still, you would need to clean the electrodes. So if even a quicker solution is needed, then you need you can cover this with a headset. If the headsets usually adapt to different head sizes, and in the case if they are dry electrode headsets, then it's easier to clean up and do a quick transition between participants. Again, the trade-off here is a bit of having more participants that you can include in your experiment, and that will compensate when you do the average in your analysis for having a little bit more noise maybe in your data depending on the experimental task. Good. Now we're going to discuss the other side of it after covering the sensitive population, the limited time, and the varying head sizes and the analysis options. I'm going to focus on the amplifier side of the technology. So again, a quick reminder, we are measuring a difference in voltage between a signal electrode and a reference electrode. And this is amplified by our amplifier. To do this, we detect an analogous log signal, which will go through hardware filters to be able to do the conversion from analog to digital. And as David already explained, this conversion is like we have a grid when we do this conversion that will have the precision on the sampling interval, so the time precision, and the resolution on the voltage that we can detect, so the resolution of how sensitive we are to the voltage change. And the range will define how big of a signal we can measure. So this combination of factors will play a role when checking the amplifier characteristics for your research, but we can also think about other topics that are relevant. For example, how they receive triggers, additional sensors, what powers our equipment, the bulkiness or the easy to transport and use this equipment, and the input impedance. So I'm going to discuss a few other characteristics of the amplifiers using, again, our examples, the amplifiers we provide as examples, and then discuss a little bit of applications related to these amplifiers. So the starting point for our discussion would be the sampling rate. We can have sampling rates from 500 Hertz in the quick CGX system and increasing to 1000 Hertz with the live amp if we have 32 or less channels, 5000 Hertz with the brain amp, and up to 100,000 Hertz with the ActiJump Plus. As David mentioned, for most of the cases, we don't need to reach such high sampling rates. The trade-off is not worth for most of the research cases, but there are examples when having a higher sampling rate when you are doing some multimodal applications can be helpful. But for common research, it's common to work with 500 Hertz to 1000 Hertz, as these will cover the main frequencies of interest in the analysis. And related to the sampling rate, we have the maximum bandwidth that we can measure. So this is related again to how the analog to digital conversion happens and the hardware filters. So the higher the sampling rate, also the higher the bandwidth that our amplifier will allow us to measure. Another important aspect, we covered this on the electrode aspect, but also the amplifier, it's important to define how many channels we are able to measure with our amplifiers. So from a headset that's fixed with 32 channels, we can increase to 64 with combined 2 live amps, up to 256 channels for a very complete head coverage with the brain amps. Though, again, most cases with 64 or 128 channels might already be enough for source analysis. We don't need to go up to 256 channels. Good. And the other aspect that David already presented a little bit is the input impedance. So this is also related to signal quality when you combine it to the electrodes. And this is an important feature that we have to consider when deciding for our amplifiers. And another important aspect is the battery life. So all of our amplifiers are battery powered, and this is a way to reduce noise. If we were to connect the amplifier to the mains, this could bring noise from the mains. So it's more common to have amplifiers that are battery powered, and then we have to consider how long can our experiment be based on this battery life, and also how many participants we can make in a row, how long can our experimental session be. So for the mobile live amp, we have 4 hours as maximum battery life, but it can be connected to power banks, so there are alternatives. And this battery life, when you're using a more stationary system, it can be over 20 hours with the brain amps, for example. And already from the image, we have an idea of the bulkiness and the weight of the equipment. So the live amp is the smallest and lightest equipment, and that therefore is a mobile solution. Also the headset from CGX is a portable solution in that sense. And when you're focusing on bigger equipments that have more connections and more boxes, then this is meant for stationary setups, and then the equipment is heavier. We have a very nice article on our website, press release article, to discuss these characteristics and even some further specifications of the amplifiers to help you decide which amplifiers best fits your research. But I hope that these initial characterizations help to give an idea of what we have to keep in mind. So now let's understand that again, as in the electrodes, we have some options how to optimize the signal quality and preparation time. And with the amplifiers now, we also don't have necessarily just an expectorant to make the decision, but we have to relate it to our research. So the first aspect, the big aspect, is if the lab setup that we want is a mobile setup or a stationary setup. So when we are working with this decision, we want to be outdoors, having the portability of the system, or we want to be seated in front of a computer. There are a few different characteristics of these two setups. So for the lab setup, the space is larger, so we can have a more powerful and bulk setup, which can then be easily extended to have more channels. When you are mobile, you usually have a size limit because you need to carry this on your participant needs to wear the system. So they have to be small and portable. And in the stationary setup, we can organize the cables with more time and care. And with the mobile setup, we need to have wireless transmission to have really allow mobility of the participant. And in the last setup is a more controlled environment, so we don't have we can probably prepare the acquisition room to have less noise overall. When you're going in a mobile setup, you are exposed to motion and other sources of noise from your environment, so this is something that you need to take into account. However, the lab setup has a restriction, that's the behavior and the flexibility that you have is limited, while when you do a mobile setup, you have a more ecologically valid experiment. Let's discuss a little bit the lab setup first. So we have options in that size. So if for starting a new lab, for example, you might want a compact solution that's easy to get started with, but also have perspective to do several different types of research. So you would probably try to look for a solution that it's an all-in-one solution with flexibility to choose your electrode technology, and a practical setup or that allows you to easily expand the number of channels and combine with other sensors for EEG measurements, let's say cardiac measurements, myography measurements, respiration, blood pulse, other kinds of sensors, and also combined with other technologies, for example, FNIRS or TMS. So, and this also requires having trigger options to communicate with different devices if needed. So one example of this flexible solution is the ActiGen Plus. It's a modular system in the sense that in modules of 32 channels, you can increase up to 160. So if you start with a 32 channel system, you can easily upgrade and add 32 channels more. It is flexible to be used with all of our electrode technologies, and also has already integrated sensors, up to 8 auxiliary sensors in the front panel. And regarding the triggering possibilities, is also very flexible because it has a trigger or 8-bit triggers input, but it also has the option of a trigger output to mirror the trigger that it receives to connect with another equipment. However, if we need more channels or some special applications that require some special features from our amplifiers, then we need to pay attention to those characteristics. So, for example, we might want to have more channels, up to 256 channels. So the brain amp would be an option there via the USB adapters. So the brain amp is also modular in the 32 channel sense, but then each amplifier is a separate box, and up to 8 amplifiers can be connected with a clock synchronization. So it's a very efficient way and precise way of connecting different amplifiers. And this is a very nice alternative in a special application example for doing hyperscanning, when you have a high precision connection between 2 participants simultaneously. And it can also be connected with a dedicated bipolar amplifier for sensors. So it's a little bit of a bulkier system, but for specific applications, it's very helpful and important. Good. So we want to consider the kind of recording that we want to have, the kind of extension. So we are starting with a system where we upgrade, or we want flexibility for other applications. And now also for the mobile setup, we want to discuss a little bit what are the characteristics. So in mobile settings, you can have settings that you just want to be in a more ecological environment, but still the task doesn't require a lot of motion from your participants. And if this is the case, then probably a fast setup is what you need. And since you have little motion, it's okay to use dry electrode technology. In all of the cases, you will still want to have triggers, so having the wireless triggers options from your amplifier is very important, and the possibility to eventually connect to other sensors. So this is all offered, for example, here in the CGX Quick system. But if we have a system that requires more, an experiment that requires more motion, then we need to consider the effect of the noise and try to minimize the noise. And in that case, having the live amp is very helpful because it's also a mobile amplifier. It also allows sensor and triggers options, but it's compatible with the active gel-based electrodes, which will be better for tests that involve a lot of motion. And it also modular and allows more channels, so up to 64 channels. So examples of sport activities, sport studies, these would be the optimal solution because of the gel-based electrodes combined with the portability of the live amp. And also it has the STE Compact, which allows you to have, similarly to the ActiGen Plus, the additional sensors, a wireless trigger connection, and specifically an oximetry connection in this kind of sensor. And it can be wired using a harness, so it's very portable. Good. So when you're talking about mobile setups, we need a fast setup with depending on the coverage that we want to have, we have to consider into account what we want, and also the kind of noise that we expect. So now I will ask Shiva to start a quick quiz to see how you would choose or recommend the electrode technology amplifier depending on the research context. So I see that you're already voting. So we have we want a cap with quick preparation and cleanup for clinical population with data suitable for source analysis. What would be your choice in that case? So passive gel-based electrodes, passive sponge-based electrodes, active dry electrodes, or active gel-based electrodes. This was quite widespread answer. So considering that we want quick preparation and easy cleanup for a clinical population, so we want to minimize the intervention that we want to do. And also, this is the first tip in the question, and also that we want the data to be suitable for source analysis, so we need more channels. It would make sense to use the sponge-based electrodes, so we can have a high density with a very quick preparation. If we have the gel-based electrodes, they are an option, but once you increase the channels, and also depending on the sensitivity of your clinical population, then it's not ideal for the cleanup and the preparation. So the best option in this case would be the active, the passive sponge-based electrodes. The active dry wouldn't allow you for a high density setup, and the passive gel-based electrodes would take a long time, would be a big intervention with the participants. Please, the next question, Shiva. Good. So let's say we want an amplifier for the lab that's conducting a wide range of experiments with EEG measurements. So with computer tasks, so which amplifier would be recommended, or which characteristics we want from our amplifiers? We want the amplifiers to accept various electrodes types and sensor inputs. We want to have a high sampling rate and a high measurement range. We want to be mobile and compact. We want to have a long battery life and a high input impedance. Maybe in the ideal world, we want everything, but we have to decide based on the specific application. So what if we are conducting want an amplifier that's versatile for the lab with EEG experiments in a stationary setup, so a computer-based desk? We don't need mobility, as you already guessed, and we want to accept various electrodes types and sensor inputs. High sampling rate and high measurement range would be recommended for specific applications, but overall the minimum, the amplifiers, most of them already have enough sampling rate and measurement range for the common applications, and the battery life would only and high input impedance can be helpful, but if you have longer recordings specifically for that, so the best would be the, as you correctly guessed, accepting various electrodes technologies. I want now to discuss a little bit specific applications. When we are considering specific combinations of EEG with multimodal applications, we have to understand the effect these applications or this environment have on our EEG quality. So, example, infant research will have specific population. Sports, as I already mentioned, will have the signal noise importance that we need to take into account, and specific multimodal applications will have different impacts on our data. So when we have MRI setting or TMS settings, those will cause specific artifacts on our amplifiers, and our amplifiers have to have specific features to handle them properly. So we have to consider these combinations. So let's say the MR is one very specific combination that requires our equipment to be safe to go into the MR, which is a huge magnet. So our equipment needs to be compatible with that. So we won't be able to use active electrodes, only passive electrodes. And we need a high sampling rate and a clock synchrony to be able to then filter the artifacts coming from the EEG fMRI. We have a lot of details that we need to cover with the EEG fMRI application, so we are not going to depth right now. It's just to highlight these would be an application that we need to have high sampling rate. Another application is the EEG TMS, but in this case we have the option to use the both gel-based active or passive electrodes, and one attention point here would be having a stable cable routing, which can be adjusted, but to optimized with the combination of the TMS, and also a very high sampling rate to be able to connect. So this would be another application which having a higher sampling rate would be important from the amplifier side. We have combinations with light tracking as well. As we are running out of time, I'm going to quickly pass through this.
Yes, we'll have a chance to talk about these during the panel discussion. So maybe we can, maybe if you can close out, then we can have the Q&A, and continue this discussion later on.
Perfect. So the idea is that we have options to optimize our research depending on the requirements for each research, and then we have flexibility to combine the electrodes and amplifiers to achieve our goals with the research.
So there were several questions from both talks, so I'll try to balance them, and just be reassured for the people who are still sending questions, we will cover them at the end of the day in the panel discussion. Right? Okay. So David, first question for you is, if the ground is used to send a low voltage to get to calculate the impedance values, then how is the impedance of the ground itself measured?
Yeah, a good question. I mean, I simplified a bit. This is just one example. There are different ways to measure. So I think the easiest way to explain is in the brain amp, where you literally have 3 different impedance checks. One is you check the ground, you check the reference, and you check all the signal electrodes. And the thing is, basically, every impedance measurement has at least these 2 electrodes part of the impedance measurement, and you have to triangulate the individual contribution of each individual electrode. That's why you need to measure all 3 to see what the impact of each individual electrode is. But if you would imagine the ground or the reference being very bad, you can't measure anything. So you need at least one signal electrode, at least one signal electrode and the ground and reference to have 3 electrodes to triangulate the impact of each individual electrode. But yeah, the ground electrode will be measured as well, but basically the voltage will flow in another direction. With the EEG it works a bit differently, but in a simplest way, you need at least 3 electrodes, and they both serve as being measured and as being a voltage source.
Okay, great. This is another interesting one. I'll mix questions from both of your sessions now. This one is again for David. With so many factors affecting impedance, the measurement must be changing a lot from person to person. You know, one person has a higher body temperature or other physiological conditions. So how do you tackle this effect of the the differences?
Yeah, so there is a lot of difference, not just within the participant, but also within the electrode position. So especially if you have this high electrode positions, Paolo mentioned, if you have 256 channels, they can also get really low on the head as well. So there might be, not all channels might be perfect. And there's also, depending what is your aim, 2 ways to deal with that. One is you can spend a lot of time to prepare every single electrode as good as possible if you really need this electrode to be good and lead a lot of signals. But vice versa, if you don't have as much time to prepare, you might also just remove some of the channels in the end. That I think in the pre-processing, in later stages, we will talk about, you can interpolate a bad channel as well. If a person has a bad or some sensors didn't connect well and you didn't have the time to prepare it, it's fine usually to lose a few sensors and interpolate them for a few participants. But also in general, the impedance thresholds are an indirect measure of your signal quality. So the deciding factor is not how good the impedance is, but how good the signal is. So I would also always recommend to check not just your impedance, but also check in the monitoring of the EEG just how the signal looks, because you can usually spot a bad channel pretty easily. And as long as the sensor is somewhat connected to the brain, because we have very high input impedance amplifiers, you usually still get a good signal or an acceptable signal, even if the impedance is not perfectly low. as long as it's connected at all, at least.
Okay. So here is another question for Paulo. In general, you covered some of it, but what would be a quick summary of the cons of using a wearable EEG headset? There are the pros and the cons. What would you, if you were to give you the top two?
So the headset has the advantage of the flexibility to fit different head sizes, but it also have a few cons on the sense that it's limited in the number of channels that you have. It has limits on also the electrode technology. So the headset is fixed to one electrode technology. In this case, for example, the one I showed was a dried system. And then you have limits also in the noise that you're capturing. So if you have more motion or depending on the environment that you are, you cannot use this kind of technology. So that's a trade-off that you have with the headset.
Okay. And this is a related quick one. Does the CGX Quick Fit, does it have a high impedance and other downsides to it? Is the question.
So all the amplifiers have a high impedance, some higher than others, and in that sense, it has specific features in the amplifier side that also matches the electrodes. So when you use dry electrodes as well, you cannot measure any frequency range. You are limited to have more defined window. So that window that I mentioned before, like 1 to 50, 1 to 45 hertz. So the amplifier also will have a sampling rate that matches this. So you can see the sampling rate of the quick CGX is 500 hertz. So depending on the application, you will need a higher sampling rate or other features that are not there.
Okay. Let me ask one question which is closely related to this. A very nice one, I think. The question is, can you clarify what is the relationship between electrode impedance and amplifier input impedance? That is there some certain value range, or what is the relationship? Maybe David, since you talked about it, do you want to take it?
So basically, as I mentioned, I think I cited Kyle and colleagues. There's a committee report on how to report EEG measurements. Kyle and colleagues, I think 2014. Anyway, it's on my slides earlier. And I literally copied the sentence verbatim from the paper, where they mentioned the electrode impedance is less important for the signal quality than the relationship between electrode impedance and amplifier input impedance. And you can also, in a simplified sense, really think of it as a ratio that if you have a very low electrode impedance and a very high amplifier input impedance, you have a good signal quality. But as you saw in our example measurements, this is really several orders of magnitude difference. So we're talking about kilo ohms in the electrode impedance, target impedance levels, and mega ohms to giga ohms. I think for the sometimes even tera ohms, yeah, let's say mega to giga ohms on the amplifier input impedance. So that's maybe also important to note, because we sometimes still get this question, oh, I have to prepare the electrode to 5 kilo ohms or lower, and for 98% of use cases, we are not in MR. If you use an MR with an EEG combined with MR, then you should go as low. But for most other use cases, you don't need to go as low anymore, because the amplifier input impedance is so not astronomically high, but so many orders of magnitude higher that you don't have to prepare the electrodes as low anymore as you used to. And yeah.
And this is, for example, what allowed the development of these other technologies of electrodes. So using the passive sponge-based electrodes, which you work with a higher impedance, it's because the amplifiers have a high input impedance.
Okay. I have one quick question, and I think unfortunately we have lots of questions, but we have to follow up because we're out of time. So this is an interesting one. The question is, the person has seen electrodes for the sintered electrodes for the head channels and gold-plated channels for the reference grounds. So when you mix electrode materials, does it affect recordings? Is it possible to use?
Yeah, so two ways for that. So in our electrodes are all silver chloride, so both ground, ref, and EEG channels. There are others that might have different materials. There's technically, I think, also in the medical field, sometimes this single-use electrodes that you literally throw away afterwards, which might have also for cost reasons different materials. But what we usually would recommend is silver chloride. What's also what we're using, but there are also other materials. It's basically a trade-off between costs, signal quality, and longevity. For the silver chloride we use, that can work for many years. But an additional factor is also, it's true that especially the ground electrode can sometimes really differ physically from the other channels. That's goes a bit detail now, but for the ActiChamp, the ground electrode is technically also the reference. It's identical to the reference electrode at a basic hardware level, but it should be re-referenced to any other EEG channel electrode, because the ground, if you use the ground electrode at the same time as the reference electrode, because it's built differently and has some additional features, the signal will be worse. So we usually recommend that your reference electrodes and signal electrodes should be exactly the same, to not have any bias that the reference electrode has a different material or something. Mm-hmm. For the ground electrode, that is technically possible because it's not used in the signal calculations normally, except for the ActiChamp, but signals and reference electrodes should be the same material.
Thank you. Yeah, that makes a lot of sense. I'm afraid we have to go into our break. All these wonderful questions, there are many more that there was no time to answer, will be followed up by chat and by in a few minutes. So we will meet again in 20 minutes time, and this will be at 17:20 German time. So depending on which time zone you're at. Okay, so see you shortly to continue our exciting program. Right. Thank you.
All right, let's start. So something completely different now, EEG and analysis software and some principles. So basically, I want to take you now to the journey that we have with an EEG data set. So really starting from recording a data set, which we usually do in a specific EEG recording software. Sometimes this might be the same software that you also use for analysis, but most of the time these are separate tools. Then there are a few steps in the journey of the EEG data set which happen inside of an EEG analysis software. So for that, we have to load the data, we have to inspect it and to process it. And then the last part in the lifetime of the data set is to bring it to publication, which also means that we have to run statistics on the data. And this is usually also, again, supported by some dedicated statistics and maybe also image processing software when you create the figures for your manuscript. So what's our journey in this session now? I will focus on these three middle parts, the analysis software related parts. First, I will look into a few concepts that are good to think about when you are preparing for EEG analysis. Then I want to consider the EEG data format, because this is important when we think about loading the data in the software, assessing then the data quality by visual inspection, and also what to keep in mind when we are planning our processing. And in the end, we will have a Q&A session as we had before. Importantly, I'm not going to do now a full introduction of our analyzer software, but I will use it for the examples. So if you want a full introduction to the software, I recommend that you go to our webinar channel, and there is a video about this there. So let's focus first in this part on reviewing some characteristics and concepts inherent to EEG data and their analysis. Some might appear rather trivial to you, especially if you have done EEG analysis already. However, use this as a reminder that these concepts should be considered when you are planning your experiment and analysis. So we talk a lot about EEG data sets, but what exactly is an EEG data set? So this depends on the experiment and the context, and different things might be meant by saying that. So it could, for instance, be a single experiment, which would usually be one recording of one participant. But it can also be that a data set comprises of multiple runs of the same experiment. This could be recorded in the same session, in different sessions, even on different days. It could also be that your data set includes multiple tasks that have been done by the same participant. These are more conceptual thoughts, but at the same time, your data set could also mean it's the EEG data of one participant, but it could also be the EEG data of multiple participants. Think of hyperscanning setups, which are more and more prominent, where we look at the same time into the EEG of several people. It could also be that it's one participant, but it's not just EEG. Maybe it's also something else, like additional sensors that you're recording, skin conductance, for example. And then, of course, you can fully cross this and have both, like EEG and sensors from several participants. So generally, you need to ask yourself what you want to analyze and how. And depending on what you record, you might then need to prepare the data first so that the data set that you have in your software has the right structure and content for the planned analysis. Two more categories to mention how you can differentiate between EEG data. First, there's primary versus secondary. Primary in this context means individual recordings. Sometimes also first level is used as a description. So these individual recordings usually come from different participants completing your experiment, though it could also be one participant doing several runs of the experiment. The secondary means here it's aggregated over individual data sets. So that could be by averaging, for instance, your ERP data to a grand average, and then you have something that is kind of a group data set. So this is the second level of your analysis. You can also just talk about a data set on the perspective raw versus processed. So raw data, of course, is coming from the EEG recording machine. That doesn't necessarily mean that nothing has happened with the data yet. I'll come to that in a moment. While processed data, of course, means you have done something with the data. It has been transformed or restructured, for instance. And usually this means a larger analysis pipeline has been applied. So this was more on the meta level. Let's now look really into the details. What's inside the EEG data? So this is how EEG data usually looks. We have a curve that has time on the x-axis and amplitude on the y-axis. And each point on this curve has basically an amplitude value y that we can read out at time point x. This looks like a continuous signal. But if we zoom in, here in these 10 milliseconds, for example, it still looks kind of continuous, but this is made up of 10 data points in this case, which are 1 millisecond apart. And actually, there are just straight lines connecting them. So these are discrete data points that are making up your signal, and how far apart they are, how many there are, this is depending on your sampling rate that you use for the recording. At the same time, your EEG data curve includes some local information. So in this case, we're having here a signal from electrode FPZ, which is also highlighted on this map. But usually we do not record from one electrode, but from a whole set. And actually, David has looked into this earlier in detail. So usually our electrodes follow a specific distribution system, like the 1020 system. And each of these sensor recordings then comes also with coordinates. Where is this electrode? And the signals also come with a unit. And the unit depends on what you're recording at this position. EEG usually comes as microvolts. Okay, let's now go for the first time to Analyzer, our analysis software, and just look at a few points that I have just mentioned. So the first thing is I have here 2 data sets, as you can see, and this is in primary. So primary individual recordings, the name already tells it to you, subject 1, subject 2. At the same time, I'm also having secondary down here. And if I go there, I have 4 data sets here. And the name again gives it away. Grand average means it's a group data set after an analysis. I'm going back to primary, and now I'm opening them. So I'm opening the first data set, and you see this has only raw data. The second one has more. So I'm actually right-clicking and expanding the whole tree, and you see there is a full analysis tree here. So here we have the differentiation between a raw data set to which nothing has been done and a processed data set. Let me now open the first data set here as an example. So, and here we have it, the data, and what we see is all our EEG channels. I'm actually displaying all of them that are in this data set at the moment. So we have all these channels that are named following this convention. Then we have some EEG channels, and A1, A2 are some mastoid recordings for re-referencing. You will hear about that more in the workshop. So with that, we also know where these channels are. And what you can also do is right-click now here and go to the properties to get more information about what's in this data set. So here we have 32 channels, a sampling rate of 1000 Hertz, and also how long this recording is. If we go to the channel properties, you also get all the names again. You also get the unit of the recording, and you get the coordinates. And we have coordinates for all of these default positions in this 1020 data set here, a 1020 distribution. And you see microvolt in all channels because they're all EEG-like channel recordings. There is also EOG, but same recording unit. Closing this again. So this data set here actually has also several experiments. So we have at first here a recording of a resting state, which has just markers that are very far spaced apart. And then down here, I'm just swapping the camera shortly that you see it. So here we're having a lot of markers in the data, because then comes an ERP paradigm after. So this is this category where we have multiple tasks in the same data set recorded. Okay, now let's actually zoom into some data. So I'm just marking some data, use this zoom button here and grabbing out a channel, and now zooming in even more with the magnifier. And you maybe start to see now how this is actually straight lines connecting some dots. And you see also the dots when this cross appears, those are the actual sampling points. And if you check down here on the bottom right, when I'm on one of the sampling points, you actually see what the time of this point is and also what amplitude value it has. Yeah, so this is the data that you have actually in there that you can read out of the data. All right, that was our first excursion to Analyzer, and now I'm going back to the slides. The important thing that you have to ask yourself is, what's the level of granularity that you need for your analysis? So you need to think about what details do you need for the analysis of that you are desiring to do, and what you are recording. Well, everything you want to analyze has to be recorded. But then afterwards, maybe there are some things in there that you really don't need for your analysis. So you can actually also break down potentially your analysis a bit to focus on that data that you need for the specific analysis. There are also 2 more characteristics that I want to highlight. You already know that EEG is measured as a voltage between a location of interest and a reference point. We already heard about that. And in most cases, you will do that with reference to a single point, so a unipolar reference. This could be an electrode around the midline, like FCZ, or maybe an electrode over the mastoid or close to it, like TP9. However, this might depend on your hardware, because the hardware might be wired in a certain way that the reference electrode is given. Also, in most cases, you would maybe just use the recording hardware filters. You heard already about this, but maybe sometimes you also use some recording software filters, even though usually you would not, and this is not necessarily recommended. But the thing is, it might have happened, maybe even by mistake, so you need to know about it. Because these two things are necessary to guide you to what you are doing in your analysis later on. You need to know that these have happened already to the data. But I'm mentioning this because these things are not self-evident. If you look at the data, and even though some of the deflections might suggest, okay, the reference must be here or there, and even if the curve might be smooth in a way that you think, okay, this must have been filtered, you really need to know for sure. And therefore, you should make sure that this is documented from the recording. And maybe your recording system is also dumping this information in your data so that it's automatically stored and that you can check it. But if that happens, depends on the hardware. So just make sure you know this so that you can make the right decisions for the analysis. Another topic of interest concerns triggers or markers. I will not go into a lot of details here because there is a dedicated session on this topic, but I want to focus on what's the difference and what are you using it for. So imagine a very simple experiment. Your participant sits in the lab and you send from your recording computer and your experimental programming software, you send pictures to the display and the subject sees the pictures on the display. You really want to know when this is happening, and therefore the software will send the picture and also at the same time a marker to your EEG data indicating this exact time point. Maybe you also have a response in the experiment, maybe a button press. Also, that will be marked in the same instant in the EEG data so that you know when it happens. Usually we speak of triggers when we are on this hardware part of the pipeline here, and we speak of markers if we are looking into the data and what was put there to indicate when the stimuli and the responses happened. So when you're planning your analysis, you need to just ask yourself, what markers do I need? Yeah. So which time points do I need to identify later in my analysis? Between which conditions do I need to differentiate? So the in this case, the number that you use and the letter, the combination can differentiate between the conditions maybe, so you can code this properly. It's quite hard to do this retrospectively, to add these markers, especially with the with the accuracy that you need for the analysis. So therefore, think about this before that you make sure to trigger these events during your recording. What is it good for? Well, in most cases, we have learned this already, you are probing your participants very often with many stimuli, and after that, you usually want to know, well, what happens around these stimuli? So therefore, you can use these markers in the data in order to cut out the data around them, and then you can forget about the data in between, which you might actually not be interested in at all. And usually we do not just one stimulus that is unrelated to everything else, but we have like a lot of stimuli in the same category, which means when you cut this out, you get not just one trial or segment or epoch, 3 names for the same thing, but at the same time, you're rather getting a condition of X trials, depending on how many repetitions you had. And also the position of this marker in the data then usually becomes your reference point, and we assign the time 0 to this point. Okay, so those were the concepts. So now we have thought about these, we can get to work with the EEG data. And therefore, first of all, we need to get the data into the software so that we can look at it at all, not to mention analyze it. So let's think about some aspects relevant here. But first of all, I'd like to do a small quiz. So Shiva, can you please launch the quiz question? There we have it. So what information must be included in an EEG data recording for software to graphically display an EEG time series correctly? So there we have the measured data values. We have the units of the recorded data, event markers, sampling rate of the recording, and electrode of origin. You can give multiple answers. Think about the question, though, carefully. What do we need to just graphically display it in an EEG analysis software or viewer correctly? So not like do an analysis, but really just what's necessary in order to show the data properly on screen based on the concepts that we just talked about earlier. All right, now we have the answers. So this is pretty distributed here. Let's look at them individually. Measured data values, absolutely. So you need to be able to pinpoint where the data point was in order to show the curve. The units of the recorded data, they're not really necessary in order to just look at the data. Yeah, if I'm just looking at the curve, at first, it's not quite important if this is microvolt or something else. If I do the analysis, then it becomes important. Same for the event markers. If I just want to look at the data, the event markers are not necessary really, but if I want to do the analysis, then of course they become very important. The sampling rate is absolutely necessary because with the sampling rate, we are able to say, okay, how far apart do the data points need to be? So this is really important. At the electrode of origin, this is also quite important because if we don't know from where the signal is coming, then we can also not show it in the right way. We cannot give this information to the user, what we have recorded here. Yeah. So the first, and the last two. The first and the last two are the ones that are strictly necessary to display the data. The other two are coming in importantly if we are going for analysis. All right. Now we revisited what should be in the data. So let's look at the data. First, an example. Our own brain vision core data format, so the brain products native format, comes as a file triplet, actually. The actual data points, they are in the file with the .eeg extension. This is a binary file, so you need a specific software in order to interpret this. The header file comes with the meta information. So that gives all of this, what channels are there, what coordinates do they have, what's the units, what's the sampling frequency, and so on. So everything we need to know to reconstruct the recording. And the marker file, pretty obvious, contains the markers that you have recorded. Another example, the EDF or EDF Plus format, the European data format. This is actually not from a specific manufacturer. This is a public format, and a lot of manufacturers include a reader or an export for this format in their software so that you can easily transfer data between programs. Consider this a little bit like a lingua franca of EEG data formats. So something that everybody can use to communicate with each other. In this case, different EEG softwares. Remarkable here, just one file. So all the information, the meta information, the data is in a single file in this case. And the plus says if there are markers in there or not. So there are many, many EEG formats, and therefore this can go up from 1 to X number of files. So it really depends on what is used by the hardware that you are using, what is created by this hardware. Our analyzer software, for instance, is able, of course, to read our own native format, so the Brain Vision Core Data format. Recently, we also added a new format, the Brain Vision Recording format. This can be read as well. And then I put some of the most commonly used EEG formats here on the right. There is a full list of around 50 data formats that Analyzer can read without problems if you follow this QR code to our website. So let's think now about the general process behind loading the EEG data. So the goals might be clear. We want to look at the data, and therefore we need to correctly display it. And therefore we need a software that can interpret the data. Let's think about this step by step. So let's say we have a software 1, and this software can read data formats A, B, C, and D, so quite a variety. If I now have the data and give them to the software will check, can I read this? And if yes, it will display it. Great. How about now you come to your software 1 with a format E, so something that it cannot directly display. Well, it will try to read it, it will fail, so it cannot display it. So now you have to think, what can I do if I really want to use this software? The first thing you could think of is converting your data. So maybe your recording software from your hardware is already able to output different types of software, of formats. So maybe you can check again there, oh, it supports also A, B, C, or D, and then you just re-export it, and nice. If not, you can think about using another software too, as a converter tool. So for that, you need a software that can read both E and output A, B, C, or D. In our support work, we actually use EEG Lab a lot for this, because EEG Lab is a community developed tool. It therefore has a lot of supported formats, because if a user wants to read a specific format, they often program a reader for it. So if you can do that, great. What if not? Well, then you have to think again about something else you could do. So maybe your software allows you to simply parse the data from a matrix. Let's think about a format F, where we have samples in columns and channels in rows, or the other way around. So if your software has now something, a utility that can just read the data from each cell, and you just tell the software what's in which cell, so in which column and in which row, then that's fine. In Analyzer, again, we have an example for this. There we have the generic data header which can be used to create a header file for such a matrix data set, and then you can read it. If not, well, then you really have a problem. Now you really need to consider, can I maybe record my data in a different format? Might not be easy because you have a specific hardware, so you might have to consider using a different software. A different software for analysis, of course. Okay, that was the general process. Let's now look at a few examples. First, Analyzer. How does Analyzer read the data? It's very particular, actually. So the software is creating a workspace. A workspace is just a collection of 3 different folders for the raw data, for history files, and for export files. History and export files do not exist from the beginning. And what we do is just give these paths to Analyzer, and then it writes them in a workspace file. And then we enter our data sets into the raw data folder. So the subject 1, EEG, header, and marker file. And once this has happened, Analyzer realizes via going through all of its readers, oh, I can read this, and it creates history files in these formats. And in these files, it will save everything automatically that you're doing with the data, and you do not have to actively save it. Let's quickly go into Analyzer and look at this. So there we have it. Just have to quickly change the camera again, because if you look to the bottom right here, you see actually here a name, which is the name of my workspace. So this is important. If you have a lot of data sets you work with and several workspaces, you need to check that you're in the right one. So that's why it tells you here very prominently. Then you have in the file menu here the workspace. So if you click on edit here, you see actually these 3 paths that I have created and where I have stored my data. So the data is in these raw data, in this raw data folder, and the history files are in the corresponding history folder. When I want to create a new workspace, load new data, I can just go here on new, add these paths here, and then save them in a new workspace file. If I want to switch to another workspace, I can just use this open button here and just navigate somewhere where my workspace files are lying. And you see they have this WKSP ending. You can also use this Analyzer logo button here in order to switch between your recently used workspaces. So this is quite nice if you keep on switching between several all the time. All right, so far about the workspace. Let's go back and let's talk about how another software does it. And I'm using EEG Lab here as an example because it's a super popular one. More traditional in the way that it has an import data function where you select a reader. So you have to decide yourself. There are a few multi-purpose readers like File.io and Biosig, but there are also these individual readers for formats. You might have to enable them in EEG Lab first of all to use them. And then you just say, okay, now I want to read file of format X. Once that happened, it goes first to the MATLAB workspace where EEG Lab runs, and then you can store the data in this EEG Lab native format. And you can do that with the raw data, and you can also do that at later steps after you have applied something to the data. So basically at each step you can create a data dump at this time. And then of course you can load again the files relating to different stages of your processing pipeline. So just from these 2 examples, you see they are quite extreme. They are very different in how you load the data. And with very, very many tools for EEG analysis, there might also many other ways of doing this. All right, let's with that go to the next point, data inspection. As a disclaimer, this part and the next part will be a bit superficial because I want to use this to give you a teaser of what to do, while we will have dedicated sessions on all of the topics that are coming now in the next 2 days. So I hope you will take this as a teaser and look forward to the upcoming sessions. Why are we doing a visual inspection of the EEG data? We could also just run our processing pipeline, right? We could, but we want to do quality control here. If we don't do it and we enter the data to our study that is not good quality, then we could compromise the results. Yeah, so something that is really an outlier in data quality could really completely ruin your data. It's therefore good practice that you check each data set that you recorded for its data quality. And in order to do this, you need, of course, a software. You can use an analysis software right away, or just something that can display your data, a viewer software, because you don't need at this point to do analysis yet. Ideally, we have recorded good quality data. So what is our goal with the visual inspection? The first goal is to get a feeling for your data. So you want to know maybe what's the noise profile of the data. So are there any channels in there that are noisy throughout? So maybe some recordings of electrodes were not so well because of bad impedance. Then you might also want to check if there are some portions really noisy because of big artifacts. And you also maybe want to check for the blinking and eye movements to get a feeling if the data is of good quality. This feeling for how good the data is will also potentially guide your steps during the processing. You will also probably want to check the completeness and the sequence of markers. So are they all there and are they where they're supposed to be? And In the next 2 days, there will be sessions on pre-processing, artifacts, triggers, and markers. So all of this we will look in detail. Want to highlight one session that is coming, which is pilot testing. Because think of pilot testing as a very thorough check of your data. So you record a few data sets in the beginning and make a preliminary analysis, check that everything is there. So you do this to detect problems, fix them, and avoid having to throw away data. Yeah. So why am I saying this? I just want to highlight that it's important to use this time to invest the time and effort into looking into the quality of your data, to make sure that you really add high quality data to your analysis, so that you do not lose time and money that you spend for your participants and for the time for the recording sessions, by doing this very thoroughly and make sure you really have nice data. For now, I talked about inspecting raw data. However, another type of inspection comes later when you have already applied some analysis to the data. So you can, for instance, check the data between two conditions, provided the same analysis have been applied. If you do this within the same recording, it's a within subject comparison. If you do it across recordings, it's usually called a between subject comparison. Again, ensured that the same pipeline has been applied to the data sets of both participants. And you can basically at any stage do this between processing steps to get something like a pre-post comparison. At this level, maybe the inspections are only visual and should rather give you a feeling that you are going in the right direction with your data. However, they could also be guided by the statistics that you are planning for the end of your study. Let me give you just an example for this, an analyzer. There it is. So I'm closing this data set. Here in this second data set, I have a full pipeline, and I'm just going to the endpoint of one of these branches, which is the deviance here. So this is an ERP, average deviance. What I can do now here for a within subject comparison, so within my data set, is just take the other condition, the average standards. So this is an oddball paradigm. And I just drag and drop that over here and then highlight one electrode. And now you see visually directly the difference between these two conditions. So I have very easily created for my individual ERPs this between condition difference. This can now be used for inspection of the data. It can be used to create pictures for your manuscript. So then you would probably not do this on the individual level, but on the secondary level in your grand averages. However, this data is just temporary, this display, because if I click on clear overlay, it's gone. So this is really just a visualization in that sense. And I'm going back to the slides. All right, another aspect is the visualizations, so the type of visualization, because it depends on what you are looking at, what visualization you choose. So let's talk about the classical EEG view that we have also just seen. Here we see again our data, usually on top of each other, and we look for the time in the X direction and amplitude in the Y direction. So here we can see how the signal evolves over time. What we can also do is take these four signals here and put them really on top of each other. So this is called an overlay or a butterfly plot. Again, we see how it evolves in time, but what we also see here is, for instance, how one of the signals is really going in a different direction or shows a much larger deflection at one point. So this can be used also as an outlier detection tool. You have also seen earlier these topographies. So again, these are the same four channels. I marked them here in red, but of course we're using for topography all channels we have And then we plot the amplitude values over the whole scalp. Again, I'm showing here -200 to 800, so the average of this 1 second. This is the same data that we are seeing here on top. And why would I do this? Because I want to see the spatial distribution. I want to see where there are positive peaks and where there are negative peaks in the data. Okay, I'm just going back to Analyzer again to give you a quick overview of those visualizations. So I'm opening this data set again here. So first of all, I'm having here 10 seconds of data. If I right click and then I have this switch view here, I can just go to a different type of view to see exactly the same data. So for instance, mapping view here, exactly the same 10 seconds of data, just in a different visualization. And I can go back to the standard view. And you see here all the data, the views that are grayed out, they cannot be applied at this moment just because the data doesn't fulfill the requirements for this view. For instance, we don't have channel pairs here. We only have these when we have something like connectivity data. What you can also do in Analyzer is to mark some data, and then you get transient views. So this can also be a mapping view, but there's also something like an FFT here. So I'm just grabbing out one channel to show you and zooming in. So here I get a spectrum, but the important thing is this is the spectrum of this data here that is shaded. And if I move this, it is adapting. So a transient view is something that is dynamically showing you more information about some highlighted data selection. Again, this can be used nicely to inspect the data, to create pictures, but it's again not persistent. It's temporary. If I click here on the X or I use the escape button, it just disappears. Yeah? So if you want to do a frequency analysis, you have to implement this differently, actually. Okay, let me go back to the slides, and we're coming to the last part of the slideshow, which is the data processing part. So generally, there are different approaches to how you might want to implement your EEG data analysis, and also to the software used for that. I tried to put this into 3 categories, though arguably there could be more. So let's look at the extremes. The first category would be scripting. So this can be done with any programming environment that allows you to write code. But in the case of EEG analysis, it's often using some mathematical framework like MATLAB or Python. And then you can use either tools that have already been provided in there, programmed by somebody else, or you write your whole script completely yourself. So if you do this, you have basically full user control because you are really writing the script to what is happening. The other extreme, I gave it this little bit cryptic name, one-click pipeline. What I mean with this is if you load your data into a tool that is designed to run a very specific analysis based on predefined processing steps. So you basically click a button for analysis X and the output comes out. This is the black box, basically. So you do not really know how the tool is doing this. So you have to have trust in the tool that is doing the right thing, basically. The category in between I call just toolbox. And by that, I mean any commercial or community developed tool like Analyzer or EEG Lab, which often also comes with a nice user interface. So these come with ready-to-use methods, which means you don't really have the full control here in order to say, okay, do now this operation, mathematical operation or this, but you're having methods that you are using. And often you can also set the parameters, but you can also decide about the sequence. So you still have a control about the pipeline that you are creating, actually. And there is arguably also a hybrid here, so especially between toolbox and scripting. EEG Lab is a prime example of that because this kind of software allows you very nicely to combine using the interface or using the scripting in combination with each other. So now if we're coming to the actual processing pipeline, the easiest and probably most obvious thing is that a pipeline is made up of several individual processing steps, which are applied in a certain sequence. And why are we doing this? Because our raw data is actually not usually in the right shape for the analysis that we plan. So we might have to make sure to improve the data quality by handling artifacts. You might also need to change the structure of your data to make it fit for purpose. So like getting the right trials selected and out. So I just want to provide a few general thoughts on processing pipelines. The processing pipelines, they should be built up step by step. So the steps should build up on the previous one. So therefore, you need to think about the right order. If you check many papers, you will often find that a lot of EEG papers use the same classical processing steps. This is because some things are just very common that you always do with EEG data, while others are more uncommon. The pipeline, though, should really be adapted to the analysis goal and the paradigm. So it doesn't necessarily make sense to use the same processing pipeline for all of your EEG experiments. Maybe not even for all of your ERP experiments, unless they're all very similar. There are definitely attempts in the community, like the open science community, that aim for standardization of pre-processing pipelines to make research a bit more comparable. So you will also hear more about these thoughts here in the pre-processing session tomorrow. So I hope this will also answer some of the questions you might have already now. Let me now go to Analyzer for the last time before we come to the final part of the session. I want to highlight this last full processing tree here now. So as I mentioned in the beginning, this data set included 2 experiments. It includes the resting state at first and then an ERP pipeline. And this is also because we have so many branches here, because at first this pipeline develops linearly. This is the pre-processing. We apply one step on the previous one and bring the data into a state where it's usable for our actual analysis. And then we start branching off. So first of all, we have here our ERP analysis, where we create 2 sub-branches with segmentation, 2 standards and deviants. But then you see also that the same steps come after these, yeah, because we want to keep it comparable. And then we have our ERP in the end. Then we have this node here, which separates our frequency analysis for the resting state. So there we applied a power analysis for alpha power. And for that, we changed the sampling rate. And therefore, this is like forking from this pre-processing part. And then we have, again, 2 ideally, and in this case, it is the case, they are the same, but you see one is for eyes open and one is for eyes closed, but same steps applied, again, for comparability. And as all of these 4 sub-branches here end with an average, either of amplitude or of power, you can use this for group analysis in the ERP type of analysis style. So this is actually what was used across several participants' recordings to create these grand average files here. All right, going back to my slides for final part. This last part here I called reproducibility, which is a difficult word. I mean several things with this. First of all, I want to ensure comparability, which means I want to make sure that my participants are all comparable within my study. But also the conditions within a participant should be. So this is exactly what I just showed you in Analyzer. So imagine you have these 2 pipelines and they are different with respect of a transformation here. So this is not good. Instead, you rather want this, that the same sequence and the same steps are used. Also, you want to enable group analysis. So this means you want to average across data sets. And for that, they should also be analyzed in the same way, being comparable. And here it helps you also if you do this, because then you can easily reproduce the analysis via automation across your different data sets. So you can take the analysis and apply it to other data sets of other recordings. In Analyzer, we have a tool that's called History Templates that allows this very conveniently without scripting, while in many other softwares, you might use scripting and maybe just include a loop in your script that repeats the analysis across input data sets. Lastly, for reproducibility for others who maybe want to be able to use your results from your manuscript and replicate it, you need to document the steps very well. So avoid the black box, but rather nicely write down your parameters and what you use for the processing, put that in your manuscript so that people can really make a replication. And of course, again, in the open science that we see nowadays a lot, people are also uploading even data sets and processing trees and so on. An analyzer, again, the operation infos that you have in the software, which automatically store the parameters for each processing step, can help you a lot with writing down your analysis. Lastly, I want to lean out lightly of the software analysis. So just give a quick look into statistics and graphics. So of course you want to do statistics for your study. And here it's a bit of a gray area because some software might include statistical methods, and then great, if it's the right ones that you want to use. If not, then you will need to export the data basically. And here it depends on what you want to do. Let's say you maybe want to do an ANOVA style statistic, then aggregated values like mean amplitudes might be the right thing to use. While if you maybe want to do something like a non-parametric permutation test, then maybe you rather export the full data. So really depending on what you want to do and what you have. On the graphics side, here it's probably the case that your software allows you to export graphics. They might not always have the best customization options, so often you can also export graphics in a way that you can use an image processing software in order to make them look nicer. Or for instance, if you use something like MATLAB, you usually have a lot of freedom to create your graphics. So here, really the question that should guide you is, what do I want to convey with my data? How do I use the right visualizations to convey my story and also give compelling examples of the analyses that I have done? All right, and with that, I want to end this session to just give you some take-home messages. First of all, consider how you want to analyze your EEG data when you plan your experiment. This is very important to think early on about this. Make sure everything you need, you record. So channels, markers, everything should be there. You should decide for the right tool and make sure that the data, how you record this, can also be loaded in the tool or how you can convert it. Allow yourself the time to inspect the data carefully and do a pilot testing phase if you can. Make use of the various visualizations to get all the perspectives that you can on your data. And lastly, document your data analysis procedure in a very clear and exhaustive way to have a very transparent processing. All right, and with that, I'm at the end.
Thank you, and it's perfect timing. A few nice questions have come in, and we'll take them before we transition to the panel discussion. There are two related questions asking, is the Brain Vision core data format BIDS compliant? So what's the relationship to bits?
So the format itself is not directly bits compliant, but we have a tool actually available that you can use in order to convert it into this file structure. So the people from bits actually selected our Brain Vision core data format, I think together with EDF, as one of the preferred data formats for bits. So if you have the data in this format, that's already great, but what you need is this complete folder structure, and also the JSON files that are describing your data set. And this you can conveniently do with our bits converter that's available. If you find it on our website as a link for download from GitHub. And yeah, then you can basically just run this over your data set, and it will automatically create all these folders so that your recording is bits compliant.
Okay. Another question in a little different direction is, when inspecting your data, what a microvolt range is typically recommended or useful? Would you have any value in mind?
The question is, what is meant by the range? Is it like for inspecting for artifacts and outliers, maybe? It's hard to say, because it's really something where you have to find the right balance, because you do not want to throw away too much data, but you also do not want to keep too much noisy data. So you really should assess your data that you have. And of course, every recording is a bit different. It also depends a lot on the recording environment factors. So some recordings might just be noisier based on what you're doing and what environment you record. Maybe participants are moving. Nowadays, there are way more mobile recordings. So it's hard to come up with a number, I would say. Something that is often used, let's say, in ERP analyses for very fine-grained segment removal in the end is maybe checking that it's within the plus minus 100 millivolt range, because you say otherwise it might be a blink or something even bigger. But yeah, it's rather hard to just say, okay, your data should be in this range from the beginning, from the recording, because this is really not standardizable in that way, unless you standardize the data actually based on whatever. Yeah.
Okay. Let me ask you one. We just have a minute. Let's see if we can fit it in. We've had many questions asking about the order of processing steps. Could you recommend some quick references where people could find more information in case they cannot attend or not attending the rest of the workshop?
If they can attend, then it's great, because there will be a pre-processing session tomorrow that also will talk about the sequence of steps. If not, actually, we have also published a webinar on pre-processing, I think 2 years ago. So you find it on our webinar channel that also talks about this. So you can watch that at any time. There are also some nice resources on EEG Lab website. They have this nice tutorial section there that also talks a bit about considerations for building up a processing sequence, and then also these kind of guideline papers that go into the direction of standardized pipelines like HAPL, for instance, or there's the other one, which name I always forget. So if you're looking for pre-processing standardization, you will also find a few examples like that. Yeah, I mean, those would be a few points where you can start.
Okay, and a quick one, and then we must move on. Is there a recommended software for complete beginners?
Well, it must be the Brain Vision Analyzer, of course. I don't have to say that, disclaimer, but honestly, I've seen over many years, like more than 10 years now, beginners work with this software, and because it's extremely visual, it's very intuitive to learn. You don't have to script. You get free support. We do workshops. Yeah, I have to say it a little bit biased, but it is actually a very good software for beginners.
So a major theme that was suggested by all of you was essentially how the challenges of getting started in EEG. So about 60% of the attendees today are new to EEG or have less than a year. So it's great that we can also help you answer your questions. And I'll just give you a sampling of questions and what are the common beginner mistakes? What are the important EEG basics to understand before moving on to complex analyses? What are the best practices? So before we get into all of that, I think a good starting point would be that we all, and including our three speakers, there was some point in their lives where they did not know EEG at all. And it's good to understand that we all started somewhere. And as a way to get this going, I would first like to ask, we'll start from Michael and Paolo and then David. Could you tell us what was maybe your first EEG project and maybe what was your background when you first encountered it, with the focus on what you found difficult or you found exciting about EEG when you started?
Mhm.
We will use this as a way to get into the questions we were asked.
All right. Yeah, so for me, my first EEG, I can't tell you actually when I recorded it. I was a student assistant in a department of neuropsychology, and everybody who worked there did EEG. So I was not graduated yet, so I guess I was after my pre-diploma, maybe 5th or 6th semester. And I started into this via an internship. And then, no, actually, it must have been earlier then, because the internships you do in the first 4 semesters, don't you?
Depends on the university
Depends,
again.
right. Yeah, anyway, I started with the internship, and as an intern, I was actually put on some diploma students' topic. So there was a postdoc, there was the diploma student, and then I was the student assistant for the project. And then later on, they hired me as a student assistant, and I kept on working on this because there were actually a few projects then, because the diploma student went on to become a PhD student. So I think we did in the end like 5 EEG studies in this group. Yeah, so I only knew about EEG from my lectures, and I basically got taught everything by the postdoc that was in the lab and the diploma student. So I really stood with the diploma student together in the lab and prepared the cap and everything. So from the beginning, I was starting to do cap preparations. And then they also taught me a little later also about doing the analysis. So actually we did the analysis really together. That was then after a few months that I was there, I would say. So I really got everything taught by people who have acquired the knowledge from the ones before them in the roles in the lab, because this has been a long-standing lab of people doing EEG coming from other universities where they have done EEG. So there was a lot of expertise in this lab, and you could just ask at any point anybody how to do things. And yeah, so
what would be, before we move to Paolo, what would be one thing that you remember was difficult for you when you started or you found challenging?
Definitely, I would say so on the recording side, I think that was quite nice because we did a lot of recordings, so there was quite quickly a rhythm coming in. Still, I made some errors here and there, but there was usually supervision, so that wasn't that much of an issue. But when it came to the analysis, I found it really challenging when it came to the point of deciding what's good data and what's bad data, really going through the data, checking for artifacts and deciding, yeah, this is good, this stays in the data set, while this is bad, I throw that out. That was really the hardest part for me to learn, and it took many years to become proficient in this. Yeah.
Perfect. We will come back to this, obviously, because this reflects a lot of the questions we got. Paolo, how did you get going with EEG?
I have a different perspectives. I was more used to work with fMRI, and my lab simply had a project that borrowed brain amp MR for doing EEG fMRI. And basically, I was the one in the lab that was bold enough to say, okay, I'll try to do this. So my first experience with EEG was trying to do the EEG fMRI, which is actually not
The simplest.
the simplest case. But it was very good. And actually, I contacted Brain Products at the time and the local distributor who supported me a lot. But I went from the basic mistakes like not configuring recorder properly and trying to get lower impedance, but the impedance value in recorder was off, so I never managed to get the correct impedance. To then,
Did you fry the brain amp though?
no,
That's very good.
no, I followed the manuals and the guidelines, so that part, the clock synchronization, the triggers was working perfect. Just preparing the subject that I had to learn to do properly. And then obviously, since was the whole group was experienced with the fMRI part and not the EEG part, then the design of the project was not ideal for EEG. So we did the data acquisition with a special population, so it was really challenging, the project, but the data acquisition worked in the end. But then the analysis was like, okay, how we handle this. So then we learned like you need to first have a better idea and plan properly to then do the project and analyze. So it was a fun initial experience, but yeah, a lot of effort into it. And then, of course, once you are familiar with the techniques, new projects and new ideas comes, and I started working with in different scenarios with other equipment with EEG.
Okay, so now we already have two potential solutions we'll come to. What about you, David? What was your... How did you meet EEG and what difficulties did you face?
Going one step further back, maybe. So when I remember how I first stumbled about EEG, I think it was actually popular science books I read in school already. When I was also not sure what I actually, like, what do I want to do with my life? The big questions. And basically, what do I want to study in this case? So do I want to do physics or medicine or philosophy, humanities? And basically, my idea with psychology or specifically neuropsychology was also it's all of that. It's physics, it's medicine, but it also touches upon, like, not as deep as philosophers probably, but on some like deeper level questions. That was really appealing to me. And when I first did my real EEG recording, that was, I think, also similar-ish, because I studied, or I learned a lot of theory in university, but actually I didn't have any hands-on experience, and the best way for me, because I wanted hands-on experience, like was starting as a student assistant as well. And basically also my biggest challenge, I would say, was really transferring all the theory I had. Like, but how do I do it? Like, I know what it means and the background, but yeah, which button do I press? How do I prepare the electrodes? Because at least in my university, I didn't learn about any of these. I mean, it's meant to be that way, I guess. In the university, you learn about theory, and it's not hands-on, but really starting as a student assistant and then later doing more of that, basically starting working there. I mean, earning money was also nice, but my driving motivator was really, I want to get my hands on it.
Okay.
Yeah, and I didn't know anything. I didn't know anything how to do it. I did know what it means, but basically no one taught me in university how to do it. I only learned this when I worked there, basically.
Okay. Wow. So three different views. So now let's try to give, I'm sure our listeners have all kinds of experiences as well. So maybe let's try to use this background to answer some of the questions that people have asked. So one is, how do you have advice on how all three of you have mentioned about the important role of practical experience? Can you suggest, for example, how someone can get practical experience in data acquisition and analysis? What would be some simple advice?
Not sure if that's simple, but it's basically.
Your best advice, like based on.
It depends where you're at, because I mean, for me at least, it started already like, which university do I pick? Because I knew I wanted to have a neuroscience focus. So I specifically searched through, or I got some recommendations from, basically, I mean, there were some university rankings, basically was one part. The other was, I knew some people that were in the field, was like, where do I go for EEG? Back then, choice was Constance, which I never heard before, but then I went there. But other than that, yeah, would say try to work there. Basically, as a like student assistant would be, at least for me, was the best entry. Like if you are in the university, try to get hired as a student assistant or participate in it, because I mean, psychology needs not only humans behind the machines, also humans in the machine. So you can also, I also did a lot of experiments as a participant just to see what people actually do.
Yeah. Same. I mean, it's important, of course, you get to know somebody who has an EEG system, and you might not always have somebody close to you. So, yeah, it's of course hard, but if there is someone at your university who has that and who maybe lets you look into this, but just looking into it is not really that helpful. You really need to do it. And also, I think you don't need to do the recording in order to make the analysis, but I think it helps because you get like a better feeling for how this data came together. Gives you a bit of a different appreciation for it. So yeah, I mean, for me, it was really, I kind of felt also this neuroscience thing is appealing. I wanted to do that. I want to get my hands on it. And so I just asked, hey, can I do an internship with you? And I mean, if you're going to a lab that does this a lot, and they do also have a lot of postdocs, maybe there are usually then also a lot of graduation projects where maybe somebody can need some help. I mean, we all know how much work it is to also prepare the participants for the experiment, so extra hands are usually welcomed. Yeah, but it's sometimes difficult. I mean, also from support, we have been in contact with people who say, well, I'm the only one at my uni who is doing this. We have this EEG system here, nobody knows about it. And then the best you can do is really try to network a little bit to find people who are doing something and maybe visit them.
But that's also a good point. We also get in TechSub, not just in SciSub, we also get this like, I found this equipment lying around. Yeah. And again, that depends kind of on the background you have, but it's surprisingly common, I would say, at least in the German universities I'm being more in contact with, that people leave and the equipment stays, and then no one dares to touch it because no one knows how to use it. And basically, I mean, you should not break it, of course, but basically, it's sometimes surprising how much equipment lies around when no one is using it anymore. And that's basically also how I became well versed in TechSub, because I was not afraid to touch all this stuff, or was digging up the manuals and so on for stuff people left behind.
Okay.
Yeah, I would say the experience in Brazil, we have a structure of the university a little bit different. So there we have the scientific initiation when you are an undergrad student, but it's optional. It's not something that everyone has to do. So the first recommendation would be like try to go after these programs and these opportunities to start doing some or helping some research in your university, and also participating as a volunteer, but also being like a little bit bold and knocking on doors, sending emails to get in contact with people, and then start what could be an opportunity of a project, and also assisting people around you in their projects and data acquisition.
Okay. This leads in to an important question. I think, David, you mentioned briefly. So someone asked us, and I think is the value of reading and how to read EEG papers and results. So one is practical experience. Maybe you can shed light on what role reading the literature plays in thinking about what did you do. Do you have any advice or tips for our listeners? What's a good way, like how important is it to read papers in your field?
Yeah, I find it extremely important because I mean, the literature is the collective experience of all of the people who have been doing this for ages. Of course, you have to read it critically. You shouldn't just take everything that you read for that's a great way of doing it. But if you read a lot, you will also see like how a lot of people doing things in the same way. And if a lot of people doing things in the same way and publish it, I would assume that's a good thing and you can trust this. But of course, there are also like great books from people who are very trustful resources. So I would actually start, if I get into EEG, really with these books like the Steve Luck book or the Todd Handy book or the EEG handbook that is coming out. Because these collections from people who have just done this a lot and collected also often experts to contribute, this is a really good way to get started. But then really, you have a project usually and you want to go in a certain direction. So I would really try to read a lot of papers that have done something similar. Because if this has worked for 30 people who have done a paradigm that is similar, and of course your paradigm will be something new, something original, you want to do something, find out something new, but it might still be comparable to maybe an ERP experiment with the same component, similar stimulus material, or maybe similar analysis approach. That will give you great ideas of how you can do it. So it's really inspiration, I would say, that you should look for by reading as much as you can and trying to find communalities across the papers, across the books, and get nice ideas. So I think you should read a lot.
Yeah, and in this sense, I think reading is crucial for the theoretical part of or if you're planning your experiment, your task, your analysis, everything. But on the practical side, there's specific resources that, like the books, may help as well, because in the traditional articles, it's hard to get an idea of how exactly they managed to get this going. But it's very useful to get the idea of relating the experimental design, the equipment that was used, and the analysis. So this you can get from the literature.
Yeah, I mean, the last thing maybe to add is I think there's also a balance to strike. Like, don't read too little, but don't read too much, because you can also get stuck kind of in a loop. Like, but this paper says this paper says that, and they do it that way, they do it another way. So basically, you should read, but you should also know when to read. I mean, you should read a lot before you start your experiment, and then probably read again a lot when you write it. But you should also do stuff in between. So not just reading, unless you, I mean, if you like reading, sure.
No, you're right. You have to find the balance, because you will always find conflicting evidence in every field. Absolutely.
Yeah, but basically, what you also read what you also want to do, and only change a few things, which is also maybe important. Like, do what others do and change 1 or 2 critical factors, but not everything.
I mean, what plays into this nicely nowadays, I have the feeling that way more people, I think the research publications also requested more, but also this whole open science movement, people are way more sharing nowadays how exactly they did something, especially in EEG analysis questions. And I think in recording, it's sometimes not so easy maybe. But if I remember back in my uni times, reading the papers, I very often was thinking, well, what did they do now? They gave like 2 sentences about the analysis. I have the feeling this has become a bit better.
One important disclaimer: we are at a company with an unlimited contract. We are not in research anymore.
No.
And so basically we are also the kind of the hands-on people, and so also take what we say with a grain of salt, and when in doubt, ask your professor or whatever research institute you're in, because we are similar on the field, but we might have a different field than you have.
True.
Okay. So this is a good segue. So now let's try to give. There were 3 questions that hover around one basic piece of advice. What would be the important EEG basics to understand before moving on to more advanced analyses or methods? It's very, very broad and difficult, I'm sure, but I think maybe we can start with acquisition, and then we go to analysis. Maybe some 2-3 things really you should master. What would be your advice on this topic? Who wants to? You can jump in, whoever has a first fully formed thought.
maybe I just repeat what Michael says, because he said it took him a long time to realize what a good signal means. And I was like, I still kind of struggle with it. I mean, I'm never, you can never be sure, but basically, yeah, judging signal quality and basically what a signal means or what a signal can tell you and also what a signal can't tell you. I think it's also a very broad answer, but basically knowing the strength, but also limitations of your research, your data quality, because there's also this thing, I mean, you can be overwhelmed and say, I don't see anything in the data. This is, I mean, the one end. The other end is you're overconfident and maybe also fooling yourself by only selectively or doing analysis over and over and over again until you find one that strikes you and then just stick with that. So basically knowing the strength and limitations of your research question and also data quality, I would say, before you
if you have to boil it down to a set of practical skills, what would you rank it in acquisition? Like, you know, what people should learn how to do well.
You should have seen multiple signals, EEG recordings from multiple participants from multiple research questions as well, before you can really see, okay, what is an artifact, for example, was a signal of interest, and also how many data sets do I need to reach conclusions. So don't look at too much at individual lines maybe, but only on the averages as we showed before.
Okay.
Yeah, I would say that in line with that, maybe in a more objective way, it's better to start getting used to EEG, trying to reproduce some traditional signals, because then it's easier to compare with the literature and get used to the data acquisition. So we have some very robust signals in the EEG, and it's easier if you start a project that basically does a small variation of this, so you can really relate the signal and the data acquisition steps to that. And then you try to do also later harder analysis and tougher questions.
Yeah, I would also say start easy. So we always encounter in also these events a lot of people who start with EEG and have questions about how can I do like my connectivity analysis with that. And I mean, you also had the thing, you did like EEG fMRI as the very first thing. This can be done, of course, but it's incredibly hard to start with something like that, especially if you maybe don't have somebody around who has done it before. So I would really recommend to go for something rather easy. And I mean, I've done a lot of ERP, so I'm a bit biased in that direction. But after also having done a lot of other analyses, I still think it's the most simple from the logic and also from, let's say, the understanding of the signal processing and also the implementation of the analysis. So I would really recommend to everybody do at least once an ERP analysis. And if you don't have recorded it yourself, I mean, it's great if you have, but if not, there are like loads of publicly available data sets online. I mean, you can even also from our website download some example data on ERP analysis and try this out, because this is really, even if you do not plan to do ERPs for your project, so much of it is playing into it, like the whole pre-processing logic and the conditions and so on that you need to create. It's always a good starting point from which you then branch off into the wild, so to say, and you can do whatever you like. But yeah, I would really recommend to everybody to do that. And as you said, there are so many easy signals and easy experiments with this kind of analysis. You know, if you do it and if you just get the result that is expected, because you know from 5,000 P300 studies in the oddball that this difference is coming out. If you do it for the first time and you see it, that's great, because then you really got somewhere.
Having a benchmark to know.
Yeah.
Okay.
And knowing the benchmark before you do the analysis. Not changing it after.
That's a very good take home, like a reproducible something that you know what should come out, right? So, okay. There were several questions about ERPs. Maybe I'll just, since you mentioned ERPs, unless you have anything else to say, I'll just
No.
a couple of tangential questions on ERPs. What if you have to? This is again a big topic, but what would be some advice on a good experimental design for an ERP? Sorry, it's not an easy question.
No.
But if you had to, like precision, or maybe you have some experience, like what to pay attention to.
I think one important thing, especially if you're starting, is that I think you already mentioned this, but only change one thing in your conditions, between your conditions. And this really means like even the visual stimulation is the same, just the instruction is different. So you can have a cognitive task based on basically giving different instructions, but the stimulation is the same. And this really, you make sure that you are really manipulating just the condition and not having other variations. So that's like the main thing for me when you're doing ERPs, is trying to really isolate and just manipulating the aspect that you want to manipulate and not let other changes affect the comparison.
Yeah. It's the prayer that I heard so many times from the person who taught me EEG, always said, like, we have to be process pure. We can't change all these things, then we don't know what's actually driving the difference. Yeah, I completely agree.
And I mean, another very broad thing is still to randomize or control or equalize as much as possible, because there might be factors in your experiment that actually produce your effect that you might not realize. For example, if one of the stimulus categories is brighter than the other, then people might blink with their eyes a little bit. Or if you happen to record your one group more in the morning and the other more in the afternoon, then one is more tired. Or even if you have different experimenters, maybe one experimenter is very fast in preparing the participant, the other is a bit slower, or one is an attractive one, another one is an ugly one. And people react very differently to all kinds of things. So try to either equalize, so basically the same stimulus, same experimenter, same time, or randomize across your conditions. So half starts early, half starts late, or half starts with stimulus A, half starts with stimulus B, or half react right, half react left. So basically, all the decisions you make, think about what if you could equalize them, randomize them, or balance them between conditions.
Just to add to that, you have to be careful not to create too many cells in your factorial design.
Yes.
Because of course you can balance everything out, but you do not want to end up with one person in each cell in the end. I mean, that's now an extreme example, but is really, if you have so many factors in there that you fully randomize, it's great if you can achieve that. But if in the end there are like comparisons to be done between some of these factors and in the cells are just super few data sets, then can you really draw valid conclusions from that? Then you just have to record and record and record. And I mean, nowadays a lot of people do that. Data sets become bigger and bigger, but that of course means more and more work. So
this is a great place, because we just got a very nice question here. We just talked about ERPs, and the question is, do you have any suggestions on how to conduct resting state studies? Because I think it's another somewhat deceptively easy to run. Do you have experience with resting state to give our attendees some suggestions?
So I think another point to point out, we will say something, but I think in the next days we will also have some like how to pilot or how to run a study, which will also touch upon this. But for resting state specifically, I would also say control at what time you do it and what substances people use before. So if one drank coffee or has a cigarette, especially, and the others don't, that might impact resting state even more, maybe. Also be careful also basically about the environment. How do people stand, sit, like, are they comfortable that they are not, for example, sitting like we maybe, I mean, it's comfortable, but it's not super comfortable, this chair we're sitting on, that you also ask participants. And I think also vice versa, one thing that I think is true for all experiments, do the experiment yourself, because only then you might realize, oh, wait, for example, oh, the chair is not comfortable, or this instruction doesn't make sense or takes too long. So being a participant in your own experiment before you run it with others, or it might be useful, or also ask some of your colleagues maybe, hey, can you help me pilot this experiment? Because while there are general advice as well, what to look out for, I think you yourself testing it and or piloting it with some colleagues before doing a full-scale study is also always a good idea.
Yeah, and for people who are attending.
Oh, sorry. Just to add one thing to this also. I would start simple here, because resting state, a lot of the people might then want to go very far to like connectivity and really see how during rest the whole network reacts and so on. I would also here start simple is an important thing. Really do the classical eyes open, eyes closed thing in the beginning to see how alpha power reacts. This is also great proof of concept, so to say, and also an easier analysis to start with. And this can be very easily added to any kind of resting state recording that you're planning.
Okay. And just to tell everyone, tomorrow Tracy will be giving a full session on pilot testing, which will cover a lot of these. And so now let's change direction a little bit. If you're listening, please send us your questions, and I will ask right away if you have any. We had a huge number of questions about challenging experiments. So, that's where the simple ERP is no longer an option. And it's really, it's beyond our scope to give advice on these, I think, but maybe we can just touch on a few. There were several questions about the multimodal research, combining EEG with something else. So maybe since you all have so much experience, maybe we can just touch on each, and you can mention for people who don't know what it is, what's the benefit from combining it, and maybe what are the difficulties or things to keep in mind. The first is EEG and virtual reality. Do you have any advice, or for people who don't know, maybe you can mention a sentence or two about what it is and what it's good for, and yeah.
So maybe I start, because in my previous life as a scientist, I did only a short pilot study where we compared the same stimulation in VR to a classical 2D stimulation, and basically found that also emotion effects were increased in VR. But again, one general advice I would also give, be paranoid and trust no one and nothing. It's basically because in that sense, what we also control is, for example, that the size of the stimuli in VR is the same size as the size of the stimuli in this 2D. Because in VR, you have this huge field of view, depending on which VR headset you have. But this is something to keep in mind, is how big your stimulus is. That's in VR not as easily controlled, because people can literally move around, and if they are nearer a stimulus, it's just bigger, and then also the effect will be larger just because the stimulus is larger, not because of your research question maybe. That is one thing. The other is latency, which I think is also a thing with a lot of things, that VR might have a different latency, so the time it takes for the stimulation to appear or something to change might be different in VR, because VR also employs some techniques, to decrease, for example, motion sickness, and also tries to have a low latency, but that your triggers and your actual stimulation is in sync. You might want to test it externally. For example, what we did was using a photodiode, literally flashing black and white in the VR headset with a photodiode, and on the 2D screen to check if the latency was different. And I mean, a very obvious mechanical problem is maybe that you have to wear the VR headset somehow and together with your EEG, and there are various ways to deal with it. Some have some headsets have a configuration where you can wear them without pressing on the sensors, but if you press on the sensors, then it's still possible, but you might want to check that, for example, if you have a head strap literally on top of the head, that the sensors below are not squished out completely. For example, then impedance checks might become more important, that you check that the impedance here and here doesn't change or is similar, or you might also not have a long experiment because people might get fatigued faster in VR.
Okay. And we only have a few minutes, so let's do a quick tour. And if you have further questions, just contact us and we can ask more. So let's go to the next combination is EEG and eye tracking. And what would you, if any of you have experience, what would you say about EEG and eye tracking, combining them?
I guess like what's common in not just EEG eye tracking, but with previous and old multimodal techniques is having the proper triggers, so having the proper connections to then synchronize the equipment, analyze them afterwards, and also having a question that justifies combining the techniques. But in EEG eye tracking, it's actually, I would say, a relatively easy combination because we have now several options, both from the eye tracker side and the EEG side, on how to communicate them, and even to load data together in Analyzer. And then it's also good because it's a very powerful tool to combine to control the behavior of the participant. So the eye tracking gives you a lot of information to make sure that during that task that you presented on a screen, the participant is actually looking at the point that you expect them to look and behaving in the way that you expected. So it's a great combination, and you just need to pay attention on matching the triggers between them and doing the design of the experiments that matches the analysis in both conditions.
Okay.
One thing is eye movements can be a source of artifact or a source of signal as well, because usually in EEG you don't want eye movements because that also produces signals that look like, I mean, they don't look like EEG but are recorded in the EEG, which you don't want. But if you want eye tracking and people actually looking somewhere else, then it's also a signal of interest.
Yeah. Then we have a nice question that says it's about EEG and ECG. That can it be helpful, like if you learn EEG, does these concepts transfer over to ECG and vice versa? You know, suppose the ECG is part of the signal you're studying, not just an additional measure. Do you have any advice on ECG and
ECG being heart activity, maybe?
Yeah.
Electrocardiogram.
Yeah, I mean, generally, there are also EEG caps that already can, like with the dangling electrodes, record the ECG at the same time. This already gives you maybe the hint that the signal must be very similar if it can be recorded by the same device and kind of electrodes. It is also similar in like the resolution, and you can apply similar analysis steps to it. Of course, it has a very distinct shape, the signal, and yeah, you would treat it a little bit. You would, for instance, not filter it in the same way necessarily as you would filter EEG data. But generally, it really depends on what you're doing. If it makes sense to record it, I would say that there are certain things where it's really very important to record. I mean, in the EEG fMRI settings, for instance. But then many people looking into emotion research or into introspective effects might also be interested in getting this. More and more people are using, for instance, the peak of the ECG signal, the R peak, to actually kind of create ERPs based on this and look really into this marker coming from inside of the participant, and then check what is the EEG doing in this. And so there are quite a lot of things to do that, and then of course the whole classical heart rate variability things, which is analysis you would do on the side not really necessarily combined, but I think there's just a big field where people want to use both of these.
Maybe just as a completely different topic, because in tech sub, on technical support, we sometimes deal with people not being sure if their equipment works and not having usually we recommend you recording a test signal with a signal generator. If you don't have a signal generator, you should all have a heart, which is the best, or not the best, but the easiest way to have a signal generator. You can literally grab ground and reference on one hand and pinch the other electrode on the other with another hand, and record your heart, because you should always see your heart as a signal generator. I actually also tested this we had a customer asking that wanted to record ECG on the foot, so you can actually record ECG from your toes as well. So basically the heart is basically your strongest signal generator. You see it everywhere on the body, even on the toes. You must. I mean, it should reach your whole body as well, right?
That's a good point. Unfortunately, we have run out of time, but we have one question from that just came in, and then we will have to close. It's a question about, I think an important one, is about the baseline, not just about the ERP, but in general. So let me just read it out. What is typically used for a baseline, and what do you do with it during the analysis phase? So if it's not an event-related study, for example, do you have any? I think it links to many things you all have mentioned, but maybe you can say something more.
Yeah, I mean, you can, if it's not a baseline in the sense of an event-related design, then of course you can easily check within a trial how the signal behaves. But this also works, for instance, in a more block design where you do something like a resting state, let's say, and you have in the beginning a baseline block that you then use to compare against the other blocks. So you can kind of take, I don't know, let's say maybe you have 30 seconds in the beginning, and then you have 30 seconds of eyes open, eyes closed, and so on. You can compare them with each other, but you can also compare all of the blocks later against this baseline and see how is the level of the oscillations that you're investigating changing over the course of your experiments, so to say. That's like one option. So we sometimes get customers asking about this, can I use a common baseline period that's before all of my trials, especially when people are using something like long stimulations, like watching video clips or something, where this classical 200 milliseconds baseline doesn't work so well anymore.
Or vice versa, if you have a lot of simulations in short succession, you might have effects longer than you think. So if you simulate every 800 milliseconds or so, then your 200 milliseconds baseline might still have the effects from the previous simulation.
Generally, if you use something like this as a baseline, it's often going to be probably in oscillatory activity analysis, so spectral analyses. Then for the baseline, the same applies as for the times that you want to investigate. Just make it long enough that it captures the oscillation of interest well. So if you're looking into rather slow oscillation, know how long a period of the oscillation is and make sure that enough of these periods appear in the baseline so that you get a good estimate. That's like the bread and butter in this kind of analysis.
One more thing, because that's something I did wrong in my PhD, if I share some mistakes. First, I used the wrong filter at first and filtered forwards and backwards with a too strong filter and distorted my baseline. And then my baseline to peak measure was wrong because basically my backward filtering pushed some of my signals on my baseline. So my baseline was not 0, but shifted. We'll talk more about this in the filter section.
Unfortunately, this is all we have time for today. I would like to thank you, the panel, for all the talks and as well as just sharing all the advice, and to all the listeners for sharing and sending all your wonderful topic suggestions, which we unfortunately just couldn't get through all of it. All right.
Bye.
Bye. Bye.